So good morning, everyone. My name is Ian Oswald, and over the next 3 hours, I will teach you high-performance Python. So the goal for this tutorial is to get you writing faster code for CPU-bound problems. Specifically, we're not looking at network-bound problems, and we're not looking at algorithmic choices. I'll mention some algorithmic choices. There's a whole world of thought to be had behind choosing the right algorithm to solve your problem. Here I'm assuming you've got the right algorithm. It runs, it takes all of your cores, it maxes them out, and you want it to go faster. And we'll look at ways of going from an order of magnitude faster with Python through to maybe 300 times faster, at least on a high-spec laptop like the one I've got here. And in particular, we're interested in tasks that can either be compiled down to C, so they run serially faster, or we can parallelize them across multi-cores and multi-machines. And we're going to start off by looking at some profiling as a way of understanding where the problems really exist. And a quick note about me. So my name is Ian Oswald. I'm English. It's a Hungarian name. I've been an artificial intelligence researcher in industry for 13 odd years. I had a big background in C and C++ in an artificial intelligence research company. And then I switched to Python somewhere along the line. One of the foreign team members gave me a bit of Python and said, hey, we need this extended. I looked at it and thought, but Python's ridiculous. It's so slow compared to the C++ that I'm senior programmer with. In the space of a day, I extended the sax parser they gave me and realized that I was more productive at the end of the first day using Python to parse sax than I was after 5 years as being senior dev using C++ for related tasks. And that was a bit of a wake-up call. And so I've now not looked backwards from moving into Python. EuroPython last year, I taught this course, and I've also demonstrated things like Pycon, which I'll mention briefly at the end, and Hedroid, the little face-tracking robot head. It was quite fun to build. I've lectured at university a bit. I'm co-founding a new startup, which I'm demoing in Startup Row tomorrow, called StrongSteam. I'd love it if you come along and have a chat with me. And some of you may have seen Show Me Do the video tutorial site. I'm one of the co-founders of that site as well from back in the day. I would like to take your photo, please. So at EuroPython, I had lots of happy people, and I was really happy. So can you all please smile and wave? Oh, let's try. There we go, smile and wave. Perfect. Thank you very much. Okie doke. So the photo will go into the updated book that I'm putting together. So after EuroPython last year, I wrote up a 55-page free PDF, and I had it printed out, just one copy. You're welcome to have a look at it. I'll be updating the book from today's tutorial, and then it'll be the free download still, and hopefully I'll get it finished off in Lulu this time, and anyone can buy a printed copy if they wish as well. And your photo, your smiling mugs will be there at the front. I posted up about the prerequisites, which I hope you've all got installed. Don't worry too much if you haven't got all of them installed. We focus a bit more on Python. Everything else we use, but we kind of move through it all at a fairly quick pace, 15, 20 minutes per chunk. So if you haven't got one of the items installed, just buddy up with somebody around you and it'll be fine. At this point, I'll just check. Has everyone got most or everything installed? Is everyone comfortable that it runs? Question? Yeah? Oh, no, you're happy. Perfect. Any problems? Hands up for problems? Oh, I couldn't hear you. Say again? I don't actually have any of it installed. My boss was going to come here. All right. Could you buddy up with somebody? That would be the easiest thing. It's certainly a bunch of this. It will be very practical, transforming the code that I've given you at the beginning and working through it. So it's easier to have two pairs of eyes and hands, I think, working on the problem. And which teaching assistants do I have? I've got Mark here. Mark, and Francesco, perfect. Okay, so we've got two high-spec Pythonistas in the room. As and when problems occur, these chaps are happy to help out. Okie doke. So before we start, there's an interesting point that came out of a senior chap at Microsoft. he makes the point that if you compare compiler optimization technology and how it changes over the years with hardware technology improvements following Moore's law, the improvements we get from compiler technology improvements by themselves is very minor compared to the improvements we get through hardware. So he says, don't really focus on the improvements in compiler technology. And it's absolutely true when you compare things like straight GCC compiling code and making things faster, but it ignores some of the compiler changes that can hang off the underlying hardware changes, things like auto-vectorization, making your code run across multiple cores at the same time. I find this just an interesting point that we can't just rely upon the compilers making our code run faster. We have to think beyond that, either using the hardware, so multi-core, which Python supports, but out of the box you don't get great support for multi-core and multi-machine architectures, and it doesn't tend to take advantage of things like parallel vectorized cores on machines. So we have to do a bit of thinking. And so multi-core, the big point of this is multi-core is very, very common and will become increasingly common. When I gave this talk at EuroPython, I mentioned that 2 cores was quite common and 4 cores will be common. I've got 8 cores in my laptop. Just as a matter of interest, does anyone have a 1-core machine with them? Anyone have a 16-core machine with them? Yeah, 16-core? Yeah, so fair point, right. So multi-core is just the way it is, and we can't, via Moore's law, it becomes difficult to shrink the size of transistors down without increasing the current requirement, which increases the heat output. It's much easier just to stamp identical cores and lay those down in silicon. So we're going to see more and more cores, so we need to think about using those cores. And technologies like CUDA and OpenCL, they are going to become increasingly common as well, and we'll touch on those towards the end. I'll just ask generally, am I speaking too fast? I get pulled up on this. No? Fast? No, I can't do faster. I will do faster, but I'll get in real trouble. So if I talk too fast for anyone who's not a native speaker, put your hand up and tell me. I know I end up speaking fast. So I mentioned earlier on, we're not looking at algorithmic or cache choices, and we're not going to look at these technologies today. They're all very interesting, we just haven't got time. So one thing you may be wondering, what kind of speed-ups can we expect to achieve? So if we switch over to some benchmarks, which they're a bit outdated now, and there are some odd choices behind them, but they're kind of indicative. So here is a language shootout looking at multiple languages. Over here we have Python, PHP, and Ruby, so the scripting languages of choice. And down here with the tiny error bars and the very fast speed, over an order of magnitude faster than Python. So this is G++, and somewhere in here there's JavaScript V8, which is generally an order of magnitude faster again than Python, or somewhere within there. This is comparing Python 3, so not comparing Python, not comparing PyPy, and not comparing any of the technologies that we're going to look at, like Shedskin and Cython. So it's interesting to me that if you take one of these examples and work on them with PyPy or Cython, say, you can bring the speeds down to be close to the G++ speeds for a lot of the benchmarks, not all of them and not always as fast, but close. And then another benchmark from a year ago. Here a chap took a bunch of CPU generally bound tasks and looked at the Intel compiler, the GCC compiler, and CPython, and we find that 1 second, or normalized time 1, versus Python 119, 2 orders of magnitude. But then using Shedskin at the time, you get down to a normalized time of 4 times slower than C++, so within the same order of magnitude. And PyPy as well, similar kind of result down there. And this was a year ago. We can go faster now. So a quick real-world result. I was working for a physics company doing some consulting. There I taught the boss. He switched from Fortran, already had very fast physics code, simulating X-ray diffraction, to reverse engineer the physical construction of LEDs via X-ray spectroscopy machines. Big, real-world, very highly computationally bound problem. I taught him how to use Python. He taught himself how to use NumPy. Every now and again, he'd turn around and say, Ian, this is going to take 1,000 years. It needs to take a day. Can you make it faster, please? So I'd take his code. And in this case, how many of you have used NumPy before? About half of you. Cool. OK, so I took his NumPy. which ran at 240 seconds. I added more NumPy by just doing profiling that I'll show you shortly, and we get to 160 seconds. I had a little think about the algorithmic choices and realized there was an if statement that could cut out a bunch of computation. We get down to 126,000. Separately, on all the NumPy work, I tried Python integration, which we're going to look at, and I got that branch down to 90 seconds. I combine the results together and we get 80, and then I make it run with multi-processing over 4 cores, and it was the run times were quite long for each of the tasks, so it parallelized wonderfully, so 80 seconds over 4 cores went down to 20 seconds. So that was quite a nice result. So there we got an order of magnitude improvement out, and that was a day or so's worth of work for him. That kind of thing becomes very easy when you've got the right tools. So we're going to look at today running a pure Python Mandelbrot plotter example. Takes about 12 seconds to run. We're going to run it with PyPy, and then we'll get an order of magnitude speed up, just out of the box with no changes. We'll look at Python and Shedskin, and we get a further speed up. So in this first part of the talk, we're looking at around a 50 times speed up on this particular task. Whether or not this applies to the kind of problems you're dealing with all depends on the problems you're dealing with. These choices are very specific to this kind of massively parallel and embarrassingly parallelly defined problem. But we can talk about your choices later on if you want. We're then going to look at using NumPy. We're going to look at the wrong way to use NumPy, in which case the execution time goes from 12 seconds to 50 seconds. It goes 5 times slower, which is rubbish. But then we figure out how to make it go faster, and we get down to 0.23 seconds. And by using all the cores and the new p-range operator in Python, we get down to 0.04 seconds for the same task. So at that point, we're getting somewhere around 300 times faster than the original example. And we'll have a play with multi-processing on one machine and parallel Python across multi-machines. And if we get there, we'll end up running with a bunch of you on the network as well. We'll be sharing the task amongst a bunch of machines, which will be quite nice. Okay, so we've got some building blocks. You've got them installed already. You've got pure Python slow.py installed on your machine, I hope. Multi.py, that's for the multi-processing later on. NumPy vector. We're going to be looking at vectorized NumPy calculations towards the end. I'm hoping we're going to have time for that. We'll just kind of play that one by ear. What we need to do now is run the pure Python slow example and just test that it all works. So here I ran, in that window, I ran pure Python slow.py. Takes 19 seconds, and I get that result. So all of you that wish to participate in the real lump of the tutorial, the live coding, please run that now and just test that you get this up. And if we get any problems, we ought to address those right now. So has everyone run it and happy with the results? Can you put your hand up if you have just run it? Just so I know. Still running? Okay. Well, that's fine. Okay, is it still running? All right, has everyone's run now? 50%. My God, how old is that machine? 42 seconds. 42 seconds. Okay, so I deliberately upped the configuration for this because I'm running it off of an 8-core, very recent laptop. Yeah, I probably should have downclocked it a little bit, knowing that there'll be a variety of machines in the audience. So, well, anyway, it'll go much faster shortly, and that's all that matters. So, does everyone have a sane output that looks like this, or at least everyone who's finished?
Where does the image come from?
The image comes from the Python imaging library, PIL. So let's go back to what was the tiny URL? It was tinyurl/hyperf2. So yeah, so tinyurl.com/hyperf2. That'll take you to the community page, and that's got a link to the source code with the 4 files zipped up. You didn't get anything? If not, there was a USB stick floating around. Is that still floating around? Could you pass that one over to the chap at the back? No. Ah, okay, that definitely shouldn't happen. What's your OS? Mint 64-bit? Ah, so I had some problems at EuroPython last year on 32-bit machines where there were rounding errors in the complex double calculations. The assert is there to check that that doesn't happen. You can turn off that assert. You'll still get, visually it'll be the same output, but computationally it's a slightly different number. Just comment out the assert and run it again. USB, chap over there with the blonde hair, do you need it still? Did you get the source files? You got them? Oh, perfect. Okay, good. Right. Okay, so then we've got the basics. Right. So then, what we want to do is discover where the slow bits in the code are. So we've got a new line to run. So I want you to type in this line here. Python -m cprofile with a big P -o for output rep.prof. So this is going to be the report.profile pure python slow.py. So if I can highlight this. So can you read that line okay? Better if I don't highlight it. Yeah? So let me just highlight that and run it in the background. So if I just run that. Okay, is everyone running that line successfully? So now we're going to use the built-in profiling module in Python to run exactly the same source again, and this time ask it to measure how long each function takes to run. And this is the first of two important tools when it comes to profiling your code and figuring out where the slow bits are. So that's finished for me. I'm guessing for some of you it might not have finished yet. Problem? I can't. Do you have the Python imaging library installed? Ah, that'll be the problem. I didn't put it on the list. Sorry, and there's a try-catch block that says if it's not there, because it didn't used to work in PyPy, then don't do anything. Sorry, that's my code from last year, hiding an error then. So just install the Python imaging library, which should be a pip install pil. So pip install PIL, or easy install PIL. Oh, good grief. Pillow? Are you on a Mac or are you on Windows? Chap at the back? Oh. So if you go into Python and just type import image with a big I, it should work. If that doesn't work, then your machine is configured in a... If it works but nothing displays, then you've got the library, but for some reason it's not configured to display, and that's something to do with your machine, I guess. Maybe we can fix that in the break. Or maybe you can buddy up with someone next to you. Sorry. Anyone have experience under Ubuntu with Pilar? Francesco? Perfect. TA springing into action. Any other problems at this point? Okay, so we want to open up Python. I'm going to start an IPython.
I think it's a version thing. On my machine, I can't do import image, but I can do from pill import image.
Oh, right. Import image should have, that's been working for a long time, I thought. I don't know. Yeah, I tend to use import image, and I've used that for quite a while. Oh, sorry, yes, and I should have repeated the question. Chap, what's your name? Walker. So Walker said maybe it's a version thing, and I don't know if it is a version thing. I use import image. Right, so now we've got 3 lines of code to type in. If you can follow these lines, please. So import pstats, p equals pstats.stats, and then the file name. Okay, you can kill it, run it again, and at the end, you put in two arguments, 300 space 300. You'll have a smaller plot with a smaller number of iterations, and that should complete quickly. Is everyone ready for this? So when you get to this point, hit return after you've typed in the last line. Everyone read that? Podium's in the way. Ah. So making it bigger wouldn't help then.
Changing the import worked.
Changing the import worked?
Yeah, from pill import image.
Okay. Okay, cool. So from pill import image works apparently. Can you not see the podium at all from where you are? Is it worth moving maybe? Or if I scroll, can you see it now? Up at the top?
I'm getting an assertion error when it just runs the profiler.
When it runs the profiler.
Yeah, an assert that failed. Something I say.
Did it fail when you ran the code first of all?
No. Just when I
Is it the assert on the validation sum? That really shouldn't happen because it's the same code being run by the same Python interpreter. Comment out the assertion. And if you want to run it faster, just run Python, just run the whole line, but with arguments 300, 300 at the end. By default, the argument that you're not seeing is 1,000, 1,000, which is big and many iterations. Just do 300, 300, and it'll run quicker. So is everyone, or most of you, at this point now where we've got the output on screen telling us about the slow points in the code? So this is kind of hard to understand. This is not an easy thing to read. So what we're looking at here is for the default case, which has got 1,000, a grid that's 1,000 large, 1,000 by 1,000 pixels, with 1,000 iterations, we run this many function calls in this amount of time, and then we get a breakdown of where the time is spent. We'll look at an easier way to visualize this in just a moment. So the whole module, when we come in at line 1, we spend 24 seconds, of course, because that's the entire module. Inside calc pure Python, we spend 24 seconds. And then we've got this calculate Z serial pure Python, which is where the work is actually being done. And then there are some sub-functions. Now, let's just have a quick look at the code. So when we come in, this is pure Python slow in gvim. So when we come in, we set up some default arguments that I've mentioned. I was just trying to gloss over that earlier on. And then we ask it to calc pure Python, and the argument true means do a display. So if you set that to false, then it won't do any pill drawing. And at the end, we get this validation sum. This just checks that we're calculating the right numbers. This is handy. This is deliberately here. This is handy because if when we're changing the code later on, you make a mistake in the code and you introduce a numeric bug, we want to catch it. The validation sum should always pass on everyone's machines. Now, if we go up to calc pure Python, all that's happening here is we're saying for the arguments that are passed in, the 1,000 and the 1,000, set up an X and Y grid that we're going to calculate over. And we're doing this in a way that I can use the NumPy code later. This works in PyPy, and this works in Python. So we've got a standard way of just building up the X and Y coordinates. And then we build up an array Q and array Z. This is the complex plane that we're calculating over. We're not going to go into what that means. It's just the X and Y coordinates in complex number terms that's used by the Mandelbrot calculation. And then this is the function that does the calculation, and here's the timing code. And if we go up here, we have calculate Z serial pure Python. This is the function that we're going to be changing over the course of this, and this is where we're about to investigate where the slowdowns are. So here we just have a loop. We go over the range, the length of Q, so the length of the input numbers. We run a number of iterations where we can break out early, and then we store an output. And this output, this line that we're calculating here, this is what we're displaying in that Mandelbrot plot. So the colors that we see there from gray through to white and the black, they're all generated by this routine here. And then when we come to display, we go into this show method at the top. And this, in this case, is using pill to convert the image into a Python array, which can be shown inside the Python imaging module. So the code's pretty straightforward. And what we're going to focus on, so the next 3 hours, is this block here. So if we just switch back to the console, we can see a couple of interesting things that come out of this. The absolute function cumulatively takes 4.8 seconds, and the range function takes 1 second out of the 24 seconds that we are calculating for. So we know that in here, abs takes 4.8 seconds, and the range function takes whether this one or this one, it doesn't break it down for us. These take a second, and yet there's about 19 seconds of calculation time that's unaccounted for. And at this point, we're a little bit stuffed because we don't get a better output in here. In a moment, we'll look at a line profile and we can break this down. So before we go on to use RunSnake, does everyone have this output running on their machines? Any problems at this point?
Would you mind just repeating what you showed there?
Repeating the code?
Taking this to the code, the statistics shown here.
Oh, okay, sure. So pure Python slow 1. So that's 24 seconds, that's the entire module, starting at line 1. And then in calc pure Python, that's the setup routine. That takes 24 seconds because the setup is trivial. 24 seconds is spent in that routine, which encompasses the calculation routine. So that takes 24 seconds. Calculate Z serial pure Python, that's called by the line above. That takes 24 seconds, and that's where all the work occurs. And we'll look at this with RunSnake in a moment more clearly. And then inside that calculate Z serial pure Python, so inside here, so this takes 24 seconds to complete. Inside here, we know that the abs and the range function take 5.9 seconds in total. And that means that there's about 19 seconds worth of code in this function that's unaccounted for. And we really want to know where these slow lines are. So let's pop back to the presentation. So, yep.
We have unaccounted for time. Is that just the nature of C profile? It's not going to tell you.
Yes. So, and that's what we see with RunSnake as well. So the question is this the nature of C profile? Do we not get a breakdown of line by line places where the time is spent? And that is the problem with C profile. It tells us which functions are slow. It doesn't tell us which lines in the functions are slow. And if you come from a C++ background, you'll know that you've profiled right down to the line and inside the line to figure out where the slow points are. Not having that tool is a massive problem when you want to really understand which of the 3 lines in your 30-line function are slow. So enter RunSnake run. This gives us a quick way to visualize the C profile output. Now, it is useful. In this case, not so much, I guess. RunSnake, let's just... RunSnake rep.prof. So if you run RunSnake rep.prof, that was the rep.prof, the output file you just generated, and RunSnake, that's the exe name for RunSnake run, that's the visualizer for C profile output. Now, in this particular problem, because the Mandelbrot problem that we're calculating is quite simple, the output is not terribly informative. All it's doing is giving us a visualization of that C profile output. So here we can see, this is where we come into the function, this is line 1 of the module, and of the things inside this function that take time, well, the next line that takes the time, we end up into this large block here, calc Z serial pure Python. So this is the for loop, which does most of the work for us. And we can see here that the abs function and the range function take some of the time in that larger function. Most of the time is unaccounted for. It just happens somewhere in there. So on this problem, this is not terribly useful. But if I give you this example, so this is from the physics code that I mentioned before. Here I was dealing with about 5,000 lines worth of Python code mixing with NumPy code. And here you can see on screen, although there is a large amount of unaccounted for time, there are several sections of this particular code base where roughly 25% of the time was spent inside these 2 sub-areas. And in there are lots of sub-functions going all the way down to NumPy calls. And so very quickly I could look at this and think, I know, First of all, I'm going to try and work on this area here because I know from my gut that these problems here, these functions here, they shouldn't be that expensive. They're taking hours of the runtime, and that's ridiculous. So I know exactly, intuitively, where to focus by looking at this output. It doesn't tell me which lines to go to, just which areas roughly of the code are worth focusing on. So there's your first take-home. When you're dealing with a big code base and you want to get a rough idea as to where the slowdowns are, use run snake run to visualize cProfile output. It's great for figuring out where the CPU slowdowns are, and it'll also visualize slowdowns for I/O-bound processes. So if you've got slow database calls or you've got slow network calls, although we're not focusing on that, it takes time, and this is a great way to visualize it. Now then, so we've just visualized that. So, as I mentioned, and as the questions have been, the question is, what's really slow inside our function? We've got this high-level overview. We need to have a line profiler. So now we're going to run these lines, please. So back in the console, you should have. Oh, go on.
Run snake run, at least on the Mac, to say this program needs access to the screen. Please run with Python W, not Python. So,
Python W is that adds that's the windowing, something to do with the windowing flag. I don't know.
Python W doesn't show the output to console.
Oh, okay. Why would that matter on a? Okay, again, yeah. Sorry, Mac specific. I don't know. Hopefully, Francesco can help. Go on.
It says slow underscore line profiler. Is that another source code file we need? Or is that
Oh, good point. Good point.
the same one?
No, it's a slight modification. Sorry, I was getting sidetracked there. So let's get rid of that. So let's copy pure Python slow.py to pure Python slow.py line profiler. And then we're going to make a one-line change. So just make a copy of pure Python slow, and I'm calling it pure Python slow line profiler. And so now we've got pure Python slow line profiler. Can I make that? I'm guessing that's too small, right? So here we've got the copy of the file. We're going to make one line change. No. At profile, we're going to decorate the function calculate z serial pure Python with one line at profile. And then that decoration is going to be used by the kernprof module in a moment. So has everyone added at profile above calculate z serial pure Python? No. We run this code, this copy of the code, through a new module which knows how to deal with that. So it's just a one-line change, at profile. So now we need.
What was the import that you used?
There's no import, just the one line, at profile. Ooh. So now we want, if I run that, ooh. So there's the line that you want at the top. Kernprof.py. Now, actually, you want to stick some arguments and then this will take too long to run. I got the result, okay. So, kernprof.py -L -v. So minus L means output the line-by-line result. Minus V, I forget. It might be for, I forget offhand. But anyway, kernprof.py -L -v, and then the modified file. If you run it with pure Python slow.py, so the one without the decorator in it, it'll run the code just fine. It'll run at normal speed. You just won't see an output. So it's not useful. What we want to do is, by typing in this line, does everyone have this line now? Does anyone not have this line? Okay. So it should run, and then, actually I'm going to run this more completely at 300 by 300. So I'm just going to run it with the arguments 300, 300 at the end, so it completes in a sane amount of time. If it runs too slowly for you, just use a smaller number, 100, 100 perhaps. So we get a small Mandelbrot plot, which I'm going to get rid of, we don't need this. What we can see here is an annotated output of our calculate Z serial pure Python function with a breakdown of the percentage of time spent on each line in the function and also the time hit in that function. So this is really useful. So we can see down here that before, we remember that the range function was slightly expensive and the abs function was quite expensive. Here we can see that the first line using range, that's not expensive at all. That's the outer loop. We wouldn't expect it to be expensive. But cprofile doesn't give us the breakdown of whether it's this line or this line. Here we can see that this range function is responsible for some of the time, but it's the inner loop. You kind of expect that. What we're perhaps a bit surprised about is the fact that the calculations on this line and this line are so expensive. Each hit is quite light, so 0.9 seconds, but in total, that's almost all of the time in the function. So that's 30, 60, 71%, plus the loop on the outside, and that accounts for all of the time spent in the function. So now we know exactly which lines are slow. And that's jolly handy, because now we know where to focus. If we look at this code, those of you who are reasonably experienced programmers, tell me what the problem is, if you would please. We've got a slow changing variable out here, and we've got a line in here that uses that variable. What's the problem? Does anyone spot a problem? Sure. Okay, I'm not going to worry about range in this context. I'm not worried about range. I'm worried about the slow-moving variable I. Can someone tell me why that might be a problem? Yes. And it's looking, so it's not only looking up twice, it's also looking up on the inner loop, which is changing quickly, and we're not modifying I in there. So we're doing an awful lot of dereferences. So what's happening here is, each time we want to get the value of Zi, Python is having to go and check out the memory location for Zi and bring the value back. And then it does the same thing again over here. Then it does the same thing for Qi, over here. And then, if this if condition isn't broken, so we carry on with the calculation to generate a lighter color in that Mandelbrot result, we come back around on iteration 2, and we go, okay, let's get Zi again. Even though I hasn't changed, then it's out here. Now, with certain technologies, like with Python that comes later on, that's less of a problem. But here, with pure Python, running in CPython, this is a problem. It's wasteful. Now, I mentioned the write-up. So if you find the PDF that's on my website later, it's just on ianoswald.com, and that's linked, I think, on the handouts that you've all got. And I'll put up a blog post in a day or two which links to all this material again. But if you find the PDF, there's a section in there somewhere on bytecode analysis. And so there I use the Python dis module, disassemble, and that breaks down the bytecode that's behind the Python code. And you can see all of the dereferences occurring. But for this tutorial, we're not going to cover that. So if you're curious about diving into the bytecode that's being executed in the virtual machine underneath CPython, take a look at the PDF. So where do we go next? So we've got our output. So here's what I need you to do now. I want you to copy purepython slow.py to just purepython.py. This will be the slightly faster version. And you're going to make a change. You're going to change the Zi dereferences to Zi without square brackets, and you're going to move those dereferences up one level out of that for loop. So if I just show you the code, so where we've got Z square bracket I equals Z square bracket I, instead we're going to make a new variable Zi, and you're going to make it up here somewhere in the outer for loop, and you're going to make a Qi variable which equals Q square bracket I in the outer for loop, and then you're going to reference it in here. So inside the inner loop, we're just updating Zi without square brackets equals Zi without square brackets times Zi plus Qi. Sorry?
If the inner iteration goes twice, you cannot do that. You cannot take Zi on one level up, right? Because
We,
if we calculate Zi in the inner loop,
oh, we're not using it in the outer loop.
I mean that we dereference by multiplying this Zi times Zi, right?
Yeah.
But then we assign the
So you're saying we can't move ZI out. We don't end up using the result of ZI, so we don't, it's local, effectively.
But you modify ZI.
Hang on a minute.
Make it a known value.
So this is what I'm after. It works, promise. This is what we're after.
Ah, yeah, okay.
Yeah, so this is the code that you want to be typing in right now. So you need to have zi equals z square bracket I, and the same for qi, and then zi equals zi times zi plus qi, and change the absolute zi reference. And then we're going to reprofile this. And this is it's a trivial change. On a larger run, you'll see a difference. When we run it with co-and-prof, you'll see a small difference. We're going through this as the process of identifying where the slow spot is and then fixing the code. Jonathan, is that readable from back there?
Yeah, I'm just looking around the 20, that's all.
Okay. So if I were to run this now, who would be upset that I'm taking it off screen? Any hands? No? Okay, you know what the changes are? So if you need to validate that it works, just run Python, pure python.py 300 300. It'll run quickly, you'll get a small output, and it will tell you that your code is correct. What I want to do is run, we're going to stick in, I'm going to stick in, I need to bring up a new copy of this, don't I? So, copy pure Python slow line profiler to pure Python slow line profiler. In fact, I'm just going to copy the one from before. So here's the version that we've got, and I'm just going to put in the app profile decorator again. And so if you can just run the kernprof module again on this version. So everyone's made that change, right? And you're running kernprof again. And then we get the new small output and we get rid of that. And so now we see the new annotated output. So we can see up at the top here that the cost of dereferencing is quite small now. In total, it's a very small amount of time. Percentage-wise, we're still spending most of our time calculating the zi squared plus qi and the absolute function down here. But if I scroll up a couple of lines, total time 3.61 seconds. That should be slightly cheaper. Yeah, 3.66 seconds. There's some noise in the results. And on a small run, we don't really get the benefits of this improvement. If you run 1,000 by 1,000 and do timings again, you'll find that the runtime has decreased for the new version. And in fact, I'll show you that. So if I just run, we remember that it took let's run it again. 19 seconds or so for the first version, and it comes in at around 12 seconds then, I think, for the second version. Is anybody having any problems with that run at the moment? Anyone have any questions on line profiling?
Yes. How can I run it in WSGI environment?
In WSGI environments. Ah,
Like a channel view, right, or anything like that, I would want to put math profile on the view.
yeah. Oh, let me just get rid of that and show the speed up. Not that one. So how would you run it in a WSGI environment? So, I've profiled behind bottle before, bottle.py. I've certainly profiled with cprofile. I don't know offhand, but there must be a way. I'm sure I did line profiling because I've run CPU-bound vision code behind a bottle gateway before, and I remember profiling that. Offhand, I don't remember, but catch me at the end. I think I think it should be possible. Ask me at the end. Okay, so now what we care about is the fact that we've gone from 18 seconds on my laptop on the big problem with the slow version. All we've done is changing the dereferencing and we're down to 12 seconds. So that's a good step forwards. Does anyone have inconsistent results with that? For all of you, it should run a bit faster with the modified version. Yes? Yeah? Okay. Anyone still typing? Want me to wait a moment? No? Perfect. Right, so now we've seen not only how to get a high-level overview with cprofile, we can get a low-level view with the line profiler module. We've identified a problem with dereferencing, which you know, if when you become a good Python programmer, you know that on the inner loop you don't want to be dereferencing variables that aren't changing particularly, and we know that we can cache those results, which is basically what we've just done. And now we've got a way of identifying it, fixing it, and measuring the output at the end of it. And that's the important thing. Whenever you're profiling and making your modifications, if you make an assumption and make a change, and you think it goes faster, it's going to come and bite you later on. You have to make the change and measure the improvement and validate the result. You can't do small runs, you have to do big runs. You have to make sure that the result is genuine. Otherwise, it will come and get you later on. Right, and so a couple of tips for writing code that's faster. You probably know most of these already, and you can validate these with the code that we've been looking at. And then we're going to move on to working with compilers. So sets over lists. If you're dealing with things like checking for whether items exist in a list, on a large list that's quite slow, on a set it's fast. Dict with square brackets will be faster than a dict.get. It'll throw an exception if things go wrong rather than dict.get, which will look up and then return a none. Built-in sort operations, generally speaking, don't try and write your own sort operation. It'll probably be slower than the ones provided in the default objects in Python. The built-in sort is optimized. There are several different algorithms that are called into play depending on the kind of data and the size of data that you've got. If you go into the CPython source code, you'll be pretty impressed at the different algorithms that are being used in there for sorting. List comprehensions. With list comprehensions, rather than a for loop, you end up enabling CPython to run the code in C behind the scenes and give you a result, rather than a for loop, which is running in the virtual machine, iterating at the Python higher level, which is slower. So if you can use list comprehensions on large operations, generally things run faster. And again, if you can use the map operation, again, that will push things down into the C level rather than running in the virtual machine level, and things run faster than with a basic for loop in Python. There's nothing wrong with using any of the other ways of doing things, but if your speed matters, do it the way that you know first of all, profile it, make modifications, experiment, make a hypothesis, have a change, measure it again, make sure the result is valid, and you'll end up making your code go faster. Not by a huge amount probably, but faster. So I'm guessing everyone's installed PyPy. Probably does anyone here not know the PyPy project? Okay, so PyPy, okay. So the PyPy project is a new Python just-in-time compiler. It's written in part by the guy who came up with Psycho, P-S-Y-C-O, Armin Rigo. There's a very talented bunch behind the project. They've got an entire different source tree from CPython, so they've got the PyPy source tree. It's Python 2.7 compliant. With it, it will run your Python code and, where possible, compile it to machine code in the background so that it runs much faster. That's the basic take-home. And we'll see here in a moment that it gives us about a 10 times speed up with absolutely no code changes, which is really quite impressive. It was a little bit controversial because for a number of years they didn't have a good output, so most people couldn't use it. In the last couple of years, it's improved massively. They're introducing NumPy support, so we can begin to do fast vectorized math operations inside PyPy and mixing it with our regular code. People are deploying Django instances and other large projects using PyPy, and people are beginning to report that, say they're running on a large EC2 cluster, they're turning off machines because the code is running fast enough that they can disable some of the machines they were paying for previously. And that's always a nice outcome for a project like this, which is supposed to make your code run faster. So don't worry about the profiling link at the bottom there. That's just telling you that with PyPy we can profile our code. So all I want to do now is just use PyPy. And I'm just going to run pure Python. So we can see that it takes 12 seconds, 12.6 seconds there to run. And if I run it with PyPy, then 1.8 seconds. So we get an order of magnitude speed up. We didn't modify that code. Python imaging library just worked. Everything just worked. And here I get a 10 times speed up. So there's a nice take home for you. If you want a quick speed up, you can worry about profiling and trying to improve your code. And it's kind of right that you should worry about it. You should at least have an overview. You should profile your code, figure out where the slow spots are, check you haven't made any really silly mistakes in your code where you're losing on a bottleneck a factor of 10 in your performance. But then, rather than investing maybe a week trying to eke out 10 or 20 or 30% from your code, switch to a project like PyPy and see if it works. If it works and you get a 10 times improvement, awesome. That's half a day's worth of trying, and it just works. How many people in the room have used PyPy already? Okay. Okay. Another question? Yes, so the same as you have to install the Python imaging library into CPython, you have to install it into PyPy as well, and that's a good point. So when I first ran PyPy, I was genuinely a bit puzzled about the idea of how do I get to use my CPython libraries inside this new environment, and it took me a moment to realize that it's a whole nother Python environment, and I have to install everything, the same as I would if I was running Jython or IronPython. It doesn't share anything. So all you do is PyPy, setup.py, install. Or I think there's a way of, I forget offhand, I think you can set up pip and easy install to use it as well. I just downloaded the source distribution and then ran PyPy, setup.py, install, and it installs pil into the PyPy directory, and then it runs. Now, one important take-home from PyPy is that it's mostly compliant with CPython 2.7. I think the language is compliant, but many people write code which is not entirely Python compatible, but it happens to work well in CPython, which is an implementation of the Python language. And there was a course, I think it was ran yesterday afternoon by Armin and Fijan and others, telling you how to convert your CPython code so that it's correct Python code, so that it runs in PyPy correctly. And it's one of those things. We use we get to use regular code, which looks fine in CPython. It happens to be an implementation detail as to why it works correctly. So there will be a couple of edge cases that catch you. There's some things to do with file handling and the with statement. I don't know, Mark or Francesco, any comments on PyPy conversion? Have you looked into that area? I don't know if maybe someone else has gone through the course yesterday and has any pointers? Yeah? Was that a question?
Well, I was just going to make I mean, I've experimented with PyPy.
Okay.
Lots of physics software. I'm getting a speed up of 40 to 50.
One of their demos is the Sobel edge detector, and they get a 400 times speed up out of it. But that's the worst possible thing for CPython's dereferencing, and the best possible thing for the compiler optimizer inside Psycho. So that's kind of, or inside PyPy, sorry. So that's kind of the biggest range. So you're getting 40 to 50 times speed up.
Some stuff.
No, it's nice. So when I was using this I was trying this in the physics company, at the time there was no NumPy support. So it was impossible to interface NumPy code with PyPy. So for me, it was a deal breaker. I just couldn't do anything with it because the boss's code was all written in NumPy. We'd already converted to NumPy from Fortran. I wasn't going to convert it again back to CPython. Now, Fijal and a couple of others are working on the NumPy project, which is the NumPy re-implementation into PyPy. They have partial support for some of the operations, so vector operations on all of the common types, they work reasonably well. I forget what the limitations are. There's a lot of limitations. It's a young project. There's also the beginning of the SciPy project, which is the SciPy modules coming over using NumPy and working in PyPy. But that's all a very young project. One thing I will say is last year I made a donation. I put up £300 towards the NumPy project, and I'll put up more money later on when they're ready for basically for SciPy compatibility. I put the money up because I think that it's quite a good project and it will make things go faster. It'll make my consultancy easier for me. If any of you benefit, they're just normal guys like us and they're living off the salaries that they're raising from the money they're raising. So if you think you'll benefit, they would certainly appreciate a donation from you. So that's my public service announcement. Okay, so PyPy is great. It's evolving rapidly. 1.8 came out only 3 weeks ago. 1.7 was a month or so before that. The NumPy support is coming along very nicely. Be prepared for some bumps when you run it. Make sure you've got a decent test environment in place. You want to validate that the code that comes out of PyPy is working correctly, the same as it does with CPython. But there's lots of help online if things don't work because the errors are generally understood now. And if there are bugs, they really care about the bugs. They really don't want there to be bugs. So if you find bugs, report them and they'll fix them pretty quickly. They're a nice responsive team. Right, now we're going to move on to Cython. So, who in the room has used Cython before? Oh, not many of you. Perfect. Okay. Of those of you that use Cython, what was your learning curve like? Would you measure it in hours, days, or weeks to get a benefit from your code? A day? Hours? Yeah? Yeah, okay, that's kind of right. And so we're going to compress that to minutes, and you're going to get it, and it's going to be perfect. So with Cython, we extract Python functions to another. There are several ways of doing it. This is the common way of doing it. We extract a Python function out to a new file. We call it a pyx file. It's pyx because it's based on the old Pyrex project, or the still running Pyrex project. We manually annotate the code, so it's like we're adding types back in the world of C and Java and the like. So we tell it that's an int, that's a complex double, that's an unsigned integer, so it can never be negative, say. The project works across all platforms, so it works on Windows, Mac, and Linux. I've used it with the physics company that was using Windows, so I use Cython there extensively. I promise it works in Windows really well. It works just as easily on Windows. I used it and taught it on the Mac last year, and I'm running it on Linux now. It just works everywhere. It's pretty mature. I've seen improvements of 10 to 100 times by compiling down to C on a single core, and then we'll go beyond that with the new p-range operator, the parallel range operator, a bit later on. And it has NumPy integration. So with the NumPy integration, NumPy, remind me again, put your hands up if you've used NumPy. Okay, so half of you. So we'll get to NumPy later on. NumPy is effectively a high-level Python wrapper around low-level C and Fortran code, and a whole mix of languages where very well understood, very well optimized libraries are wrapped up in this really nice, friendly, high-level wrapper so that you haven't got to worry about the low-level compilation details. You just get fast math, plain and simple. You put in a massive vector, give it an operation, you get a result back, and it's running at C speed in the background, nicely optimized for your architecture. So with Cython, we can interface with that, and so we can take our Python objects, push them behind the virtual machine's back into NumPy, run it quickly, and bring the result back, all in C, all compiled, and then anything that's computationally bound and was limited by Python's virtual machine implementation stack, we generally get around all of those problems. But there's a bit of work involved, as you'll discover. So we now want, you want a new directory. I'm calling it Cython Pure Python. And you're going to copy the purepython.py example into Cython Pure Python. If the kernprof decorator, the app profile, is still in there, you have to get rid of it. Otherwise, when you run it or compile it, it'll just die because we're not importing anything. So remember to get rid of @profile. And then we'll walk through the code changes. So you should all have a Python pure Python directory, and you should all have copied your pure python.py module into that directory, and then cd into that directory. We're just going to live in that directory because we're going to have several files in there. What we're going to do is we're going to make a new module, calculateZ.pyx. We're going to copy the calculateZ pure Python function out of pure python.py and into the new pyx module, just that one function. And then we're going to use Python to compile it in a moment. And so we'll look at the code. And we're going to need to add a setup.py file, which I'll show you in a moment to get the compilation working. And we're not going to get a particular speed benefit from this step, but the next step, when we start to annotate the code, then you'll see the speed benefits. So I'm just going to jump out and call up the code, and then we can follow through. So what did I call it? Python pure Python. So we've got to calculate z.pyx. I really should make that default. And we've got an empty calculate. Oops, z. So take your calculate z serial pure Python and cut it out and put it into the calculate z pyx. That's your first step. Just the straight Python code, no other change. The only change is that it's a .pyx file, not a .py file. And then, because we're now using a separate module, we're going to import calculate z. And so we need to import the module, calculate z. Just pretend it's a .py file, not a pyx file for the moment. Just import it. And then when we call it down here, because we're importing it, we have to reference the module name. So calculate z serial pure Python. So ignoring the fact that it's a pyx file, which doesn't make any sense, and it's pretending it's a py file, all we've done is extracted the function and put it in another module. That's all we're doing at this point. So that's the first bit of setup. Now we're also going to need a setup file, and I'll just copy that across. So you also need a setup.py file, which will be this file. So I want you to type this in, please. And we're going to use this for a couple of the next tutorial steps as we build things up. And if you use Python in practice, you're going to end up coming across this file a whole bunch of times. So it's better that you just type it in and get familiar with it now. So there is also a GitHub repo with all of the code there, with everything, all the variants, including some of the things that I'm not teaching, but they're all part of the, but they're not part of the, they're in the book that I'm putting together. So you could just crib it from there if you want. I kind of think you should type it in so that you're familiar with some of the options that occur. Is this monitor in the way? Or am I in the way? The monitor? I don't know if it goes any lower, but no, okay. I don't know if that helps.
So the difference between writing your own C module, importing it in, and using Python, that you can just generate that module? Are you generating the module instead of writing the straight C yourself?
Yes. So if you've got, so the question was, is importing the compiled module different to writing your own C module? That's basically what you asked, yeah? So rather than writing a C module and using, say, the C-types interface to expose it into Python, instead here we're saying I've got a high-level piece of Python, I'm going to annotate it so the compiler knows how to make it go faster, and then I'm just going to use that annotated version. So it's cheaper on your time than writing a C module. This is kind of the step in between writing your own C code, because you happen to really like writing fast C code and importing it into Python. Here we're just using, we can prototype, say, in Python, and then push it down to the Python level. Anyone still need this up on screen? No, we're good? Okay, we're going to use this in just a moment. First of all, we're going to check that the pyx file that we made is correct. So I want you to type in Python -a for annotations, and then the calculate z.pyx. And here we'll test if your Python is installed correctly. So if we hit return, you should get no errors. And if I do a quick ls, so I now get a calculate z.html file. So you typed in Python -a calculate z.pyx, and it outputs a calculate z.html file. Yep. And if we open that in Firefox, where's my Firefox? Ah. When you learn Python, you might skip this on the website, and I've talked to people who have used Python for quite a while who didn't know about the -a output. It's insanely useful. You need to know about this. So just remember that you've seen this funny display with lots of yellow lines, and then when you come to use it in 6 months' time, you'll wonder where that funny display come from, and you'll look for it, and it will make your life easier. What happens is Python annotates your Python function, and it tells you which lines it's going to convert to efficient C, and which lines are running mostly through the Python virtual machine and so are going to be not so efficient. Yellow means it doesn't know what to do with it and it runs it through Python. So if we double click it, we see the C code that it's going to generate. And if you look at the C code that comes out the other side, you can just match up this display with the C files that are generated. And what we want are lines that are, well, the only white lines here are the ones that are commented out, so it knows it's not going to compile those. Really, we want most of this file to either be pale yellow or white, which means it's all going down to the C level, none of it's running through CPython, and that means it's basically you've written a bunch of C yourself and it'll run at C speed. So we're going to use this iteratively to improve our code in just a moment. So just to check, does everyone have that up in their web browser? They've got an HTML output file? And if you double click one of the yellow lines, you get you get to look at the C code behind it, right? Any problems? Cool. So we've done that line. We've got a setup.py. Now we want the line at the bottom. Python setup.py. So it's like you're going to run the installer, which you do when you're installing a new package. Only we're going to use the build __ ext section, which is what you've just typed in, and you want -- in place. So it builds in this directory, not elsewhere. We want the compiled module to be in this directory. Ah, yes, you need to have a compilation environment installed. I think it also works with G++. Did that, when you ran Python after installing it, did it not complain about that? No. Okay, I'm sorry about that. I assumed it would tell you what it needed. Okay, sorry. So yes, yeah, for Python to work, it's using a C compiler. It needs to have a C compiler installed behind the scenes. Python. So when Python runs, it needs to have a C compiler. Python uses a C compiler to compile your Python. Oh, Python. Well, let me just check. I'm pretty sure. So if there we go. So, Python, setup.py, buildxt that you've typed in, -- in place, so compile in this directory. It tells us it's running the buildxt section of your setup.py script, and so it's building the calculate-z extension. It's found the .pyx file, and so it's building that for us. Then we get some build information. You can see it using GCC here, and then various options. If you need to debug, it's quite handy that you have a nice output here of what the compiler is calling. If you've got multiple versions of GCC, or you've got a mixed environment, like on Windows you're using, say, MingW with GCC, and you've got Visual Studio, you can end up with a bit of a mess here, and so this is handy for debugging.
Can you show the setup file again?
Ah, sure. So if this isn't working, you've got a typo in your setup.py. Anyone have a problem at this point? Problem? Yeah, no? No? And so what we want at the end, calculate-z.so, that's the output file, and that's what we're looking for. And then, so here we go. Do you need that setup.py up on screen still? Or are you good now? Maybe you could check with one of the guys on. You got it? Cool. Okay, so now we have a compiled module which can be imported because Python can import modules that are compiled. I think on Windows this will become a calculate-z.dll. So I think we're now in a position to run. Yeah. So if we just run pure python.py. Let's just check that I saved everything. Yeah, so everything's saved. So now we're going to run pure python.py, and this will run basically at the same Python speed that we had before. It's not going to be super impressive in this stage. We get to the super impressive bit a bit further on. So, okay, now it runs in 8 seconds rather than 11.9 seconds. So we get a percentage improvement, which is nice, but it's just a percentage improvement. It's nice, well, it's nice, it's very important to see that the asserts don't fire, so we're getting the same complex double precision math progression. And so now we're integrating compiled C code with high-level Python, so the imaging library that's one of the modules works still, and this is all great. Now, does this run for everyone? Anyone got any problems at this point? Do I need to put any files back up? No? All good? Yes, I did. So I added import calculate-z because we have to import the module that we've just compiled. Is not. So yeah, when you reference in the date time section, you should be referencing calculate_z dot calculate-z serial pure Python. Do you have that as well? Yes, so we've moved the code out to our submodule. We need to reference the submodule, and then we get it compiled. And in a moment, we're going to start annotating it. So good for everyone? Right, so now we need to do a little bit of work. So there's lots of help online about this, and the Python site has a lot of documentation. What we want to do is start telling Python what the objects are, what type they are. So we can tell it this is a list, we can tell it this is an integer, tell it this is an unsigned integer. Unsigned integers are helpful. The for loop will know with an unsigned int that it's never going to go below 0, for example. So it doesn't have to start doing negative array index checking. So it can turn off a bit of the safety checking code when it runs in C. And we can tell it about complex numbers. So let's start to make some of those annotations. So it's as simple as list q. Max hitter is an unsigned integer, so we can tell it. And we've got a list Z. So that's our first change. List Q, list Z, unsigned int, max iter. Okay, then we save this. And now, okay, so in my Vim, I get an error message. My God, I've put types into my argument list. What a fool I am. It doesn't know that it's a pyx extended file, which is not Python, but Python. So I'm just going to ignore that invalid syntax. So everyone's made list Q, list Z, an unsigned int, max iter. Let's go back to the command line and run the Python -a line again. So we get a new HTML output file. So Python -a calculate z.pyx. We open that up in Firefox, and if I compare the last and the next version, we see one change, line 11. So previously, it was a full yellow line with a lot of C code. Ooh. Now, it's a lightweight line. And the reason for that is simple. We've told Python max iter is an unsigned integer. It's not any other Python object. It's only an unsigned integer. So it knows it only has to treat it in a for loop as an unsigned int in C. So it doesn't have to have any code to call into Python to say, depending on the type of object it is, iterate over it in this specialized way. It just says it's only an integer. So iterate over it this way, and by being unsigned int, it can't go below 0, so it can turn off some of the checking.
What's the difference in the shading? I didn't get that.
So if there's no shading, so on this line now, it means it can compile it to pure C without any calls into the Python virtual machine. Whereas before, here we have lots of code, and it's all calling Python objects. So it's using the ref counting and calling into the Python virtual machine level, dealing with the Python objects. Because at this point, it's iterating in a for loop over a Python object. It doesn't know if that's a list object or a range integer or something else with a sequence that can be iterated over. So it's just having to be safe and calling into Python. And we want to get rid of all of these safety levels and just specialize it. So the more yellow you've got, the slower your code, the more calls into the Python virtual machine. And so we want light yellow like this here, or no yellow like this line here. Okay, so that's the first change. Now I'm going to have to remind myself. Python, pure Python, pyx1. Right, so I'll just show you on screen. The next change, I want you to make cdef unsigned int I. So this is the counter for the outer loop. We'll make this an unsigned integer. In fact, do the first two lines. cdef unsigned int I and cdef int iteration. In fact, they could both be unsigned ints. It doesn't matter in this case. So cdef unsigned int I and cdef int or unsigned int iteration. So let me copy that change over. Now I'm going to Python it again, and then we'll look at the results. And now we should have, what's changed this time? So one change, if I %1000 to print out, so that simple change there, that's now a bit of C code because we've got I as an unsigned integer. Zi abs I, we should have one other change. Above the for loop, Oh, there we go. Yes, that's what I was looking for. Yeah. So here again, the rather than for I being I any Python object which needs to be handled in the Python virtual machine level, we can now say, well, I is, we'll see here, I is just an integer. Where's that defined? Oh, it's defined, I guess, up here, isn't it? Oh, we don't see that. So that's defined as an int. And then we just iterate over it in a straight Python loop rather than, so in a straight C loop, rather than iterating over it in a large lump of Python code. One question?
Yeah, on that line, is it
Possible
possible to turn off null checks?
to turn off?
Null checks.
Is it possible to turn off null checks?
This line, it says unlikely that it sends in a null value for the list. So it doesn't handle it.
Oh, okay.
Can you say this will never be really does there if we...
From memory, yes, you can specify checking, or is that only on NumPy? There is something to do in Python with none checking. It might only be to do with NumPy. I don't remember offhand. There are a bunch of optimizations you can make to tell it more things to turn off. There are some annotations you can make, which don't help in this case, but there are annotations we can make. So yeah, but have a look up on the Python documentation. Right, so let's just measure the speed improvement. So let's, where's our setup line? So run Python setup.py build-ext in place. So this is using the improvements we've made so far. And then we'll run it again. So we had 8.6 seconds before. Now when I run it, it's probably not much faster. What are we up? 6 seconds. Okay, so we've shaved off 1.5 seconds by just doing a couple of changes. So that's an improvement. Does anyone not see an improvement? Okay, yeah. And one thing I've noticed on my Linux laptop, if I unplug it, it goes into on-demand power mode, and sometimes the timings become rubbish. Plug in the power and it becomes good again, and some other silly things. When I shut the laptop down and open it again afterwards, it seems to get stuck into run in conservative mode, and then I don't see any improvements. And I also develop in a VirtualBox quite frequently, and in there I don't do any timing, so I don't trust it at all. So here it's a fresh boot, clean install, optimal conditions. Certainly when you make some of the improvements, although you'll get rid of some of the yellow lines, you won't see a speed improvement because they weren't, although it's yellow and it's calling into the virtual machine, it's not actually slowing it down.
So when I was running pure Python, I was about twice as slow as you, now I'm slightly faster. Why is that?
You were twice as slow and now you're slightly faster.
So I mean,
Oh. Wow. I don't know with the simple answer. Yeah? Now you're catching up and beating me. Well, okay, I don't know. Good. It's the power of Python. It's coming down. So let's implement the last 2 lines, and we'll see the best improvements we can make out of this. So I'd like cdef complex zi qi. So you could have 2 lines, cdef complex zi, cdef complex qi, but you can declare them on the same line. So cdef complex zi, qi, and cdef list output. From memory, the list output doesn't make any improvement. It just gets rid of some yellow, but telling Python about the complex numbers, that gives us a decent improvement. I think that's the only change I made in here. So if I just copy that across. So this here should be the one that gives us the nice speed improvement in here. Okay, and then if we compile that, anyone need that up still? Everyone good? Okay, I'll take that as a good. So we build it in place again, and then we run it, And then, so now we're down to 4.1 seconds. Yeah. So this is pretty good. Yours has slowed down. I don't know. More yellow. Maybe Francesco can give you a hand. Anyone else seeing more yellow and slowdowns? I jolly well hope not. No. So I don't know how the yellow is calculated, and from what I remember online, they make it very clear that the yellow just says, this is calling into the virtual machine, you probably want to check it out. Beyond that, it's not an indicator of how much slower things go at all. Certainly I've gotten rid of a lot of yellow sometimes, especially when dealing with NumPy, and there's been no speed change at all, and then you find one pale line, you change that, and you get a doubling in performance. Again, it's back to profiling and measuring. It's what it all comes down to. Right, now I'm going to show you one last change, which you're not going to have to type in. Am I in the right directory? Not anymore. So, right. So I'm now going to modify my calculate Z and show you, this is as far as I was able to take it. I'll just run it first of all, and then we'll look at the code. So first of all, let's just Python it. So you can see now, in this version, on the inner loop, I've managed to get rid of almost all of the coloring. So it's almost all pure C code now being executed. And I've done that by expanding the complex math and turning it into just double precision mathematics. So we're taking away any overhead in the Python complex data type, which doesn't seem to map beautifully through to a C implementation. I've just expanded that math, because complex math is just pairs of doubles. You can do it quite easily. So I've expanded the math out. And then, so I compile this. So we had 4.1 seconds before, and all I did was expand the math. I didn't change the structure of the code, I just expanded the math. Duh. Ah, yeah, they changed the name. It's going to be my crowning moment of glory. Dangers of copy-paste typing. All right. So remember, we had 4.1 seconds before, and now. Sorry? No. The Python just gives us, that would have just changed the name in the .html output. All the Python -a does is make an HTML output. It doesn't do anything else. So 4.1 seconds down to 0.26 seconds. And that's a nice speed up. So I think out of that offhand, yeah, we get a 50 times speed up at that point. So that's a problem-specific change that I made here. By asking around online, I had people telling me that the complex compilation support isn't so brilliant, and maybe I want to try expanding the math, and so I just expanded the math. And I had the same thing with Shedskin, which I'll show you in a moment, but that's been improved in the meantime. It's not necessary anymore. But in Python, the support for complex numbers, it's perfectly correct support, it's just not as fast as it could be. And so by putting in another half hour's worth of effort pulling the math apart, then all of a sudden I get another large factor speed up. So this is very problem specific. If you're not using complex numbers, you may find you haven't got to worry about this. But if you find, let's go back to the previous version. If you find that you've got a bunch of yellow still, so like we've got down here at the bottom, and you're just wondering of ways of getting rid of it, and you're dealing with complex numbers, maybe expanding the math is the answer, at least in the current version of Python. Okay, so I hope you feel that you've learned something so far. We've gone through the profiling, and now I can show you how to get maybe a 50 times speed up with half an hour's worth of effort. It's not that difficult. Once I got past this point in the tutorial at EuroPython, and carried on with a whole bunch more stuff that I hope you're going to find really interesting. But I had one of the guys come back to me and just say, Ian, that point we got to by about the hour point, slightly running over here, he said, that's great because I managed to turn off half my machines on EC2 and I was saving $2,000 a month after that, and I just did that in the evening after the tutorial. And I took that as quite a big win. So I hope some of you are going to get a similar win out of this as well. Right, do I need to leave this up on screen at the moment, or can we move on from here? So you don't need to copy all this code. This is going to be, it's up on my GitHub repo, and you can get the better math version that I've just showed you where I expand all the math, and it's discussed in the PDF, the book that I've got. So that's all there. You can refer to this all afterwards. And I'm going to be around all weekend, and I'd love to talk about this, so you can come find me as well. Right, so let's push on. I want to get through at least, yeah, next quarter of an hour, and then I think we'll call a break, and then we'll see how we're doing after that. So one of you, Fred something or other, I can't read your name. You, sir, you asked me about bounds checking, or none checking. A couple of the flags, there's bounds checking and wraparound checking. You can turn these on manually to give Python a hint as to which checks it can disable. And you can also make choices like declaring a variable is unsigned int rather than int, and it knows, for example, it hasn't got to do negative indices checking. We can also turn on profiling support. So this is really handy. You can enable C profiling support, so we can see, at least with the function level, even though it's compiled in C, and there could be a whole string of functions you've got in a PYX file or a set of PYX files, we can still get up some C profile support for those. So you can get at least a high-level overview as to how your improvements are working. Now we're going to step on to Shedskin. Shedskin is similar to Python, but different. It's useful. I'd love it to be really, really useful, and I really wish it had managed to get further ahead or become more applicable perhaps than Python, because what it gives us is really lovely, but it has some key limitations as well. So one of the things you've noticed now with your Python code is that if your boss then says, I don't know Python and I want to edit your code, you're going to have to handhold the boss and show them how the Python works, because you've got to keep the annotations in place, check the profiling afterwards to make sure nothing is broken, and have the right compilation environment set up so you can compile it again. And that's a bit of a pain. So with Python, there is an overhead in your code development. You haven't got to just learn it, you've also got to maintain the code afterwards. With Shedskin, we can get rid of this. Shedskin is an automatic type inference compiler. So you run it over a lump of Python code, it'll figure out which types you're dealing with automatically, and it'll export C code, which is compiled in the same way that Python compiles the code, but you haven't got to annotate anything. You can give it some hints by rewriting some of your Python code. So I had at the version of the fastest version of Python where I expanded the math. In a previous version of Shedskin, I had to do that, and I can show you the result of that. But in the current version of Shedskin, even that's not required. It's a really smart auto-type inferencing compiler. So it can take a 10,000-line file of Python and spit out C++. And it'll do it automatically for you. It'll take a couple of minutes when it does it. But you haven't got to do anything else. You haven't got to annotate anything. You haven't got to profile it. You haven't got to think about it. You let Shedskin do that. Some of the key limitations, it can only import modules that have been implemented already. So for example, the Python imaging library isn't supported in PIL. So you can export that lump of code to a separate Python file and compile it, just like we did with the Python code. And you can import that compiled module and then run it in Python and use Python imaging library there. But you can't use the Python imaging library in the code that you've pulled out for Shedskin to use. And also, we can't use NumPy, and for me, that's the deal breaker. I do so much of my work with NumPy. The fact that I can't use NumPy in there, it's just a big problem. And it's very unlikely that NumPy will be supported at any point, which is unfortunate. But if you're not using NumPy, and I've got a Commodore 64 emulator example to show you in a minute, then it gives you this wonderful speed up for absolutely no effort. So, I'm guessing most of you have got Shedskin installed, so let's see if we can do this. So make a Shedskin directory, copy your pure Python code into Shedskin. I'll check I haven't got the annotation in there still. No annotation, so this is just the original pure Python code that ran at about 12 seconds, and we're not going to do anything to modify it. So I'm just going to run shedskin on it. Okay, so because the Python imaging library isn't supported, as I mentioned, we have to make a little change. So, okay. In the show function, where we import the Python imaging library, just delete that bit of code for this example. Rather than bother with extracting that function into a new module and using it separately and safely, I'm just going to compile the whole Python file. And so I just want to get rid of that module that's not supported. So I've just removed the code for the imaging library from the show method and just put a pass statement there instead. That's right. You can all see that, right? So the show method just has the one line pass in there now, nothing else. And then if I compile that, so shedskin spends a couple of seconds analyzing the types, then it generates some C++ code for me. And so if we look at the header file, there should be not much in there. Yeah, so the header file is pretty simple. You can see in here that it's extracting the booleans, integers, max iterations, and pulling these out, and the function name, and it's automatically figured out. So, calculate Z serial pure Python, that's a list of complex numbers. It's figured it out for us. This is great. And if we have a look at the CPP gets a bit long. It's auto-generated, so you end up with a lot of code in there. You can see it importing the shedskin C++ equivalent to certain libraries like datetime, sys, and time, and the pure Python function that it's just generated for us. And then there's all the auto-generated code. If you went through the Python output, you would find it reasonably similar to this, auto-numbered variable names and variable names based on the variables that you generated in your Python code. So you can follow it through. And I actually spent a bunch of time last year trying to put OpenMP support into the auto-generated code. So I just took these two files and started wiring OpenMP in by expanding all the for loops and hard coding it. I couldn't get the damn thing to work. It took me a day, and in the end on the list everyone said, yeah, it should work, but we're not kind of sure why. And it was a bit annoying. But it's still straight C. So if you want to get in there and edit, bug fix, or extend, you can pull it apart and rename it yourself. It's easy enough to follow. It's quite clean code. So the other thing it makes for us is a make file. So it's just a standard make file. So we just run make, and it pushes it through G++, same as Python was using, GCC. Say again, please? No member named unit. Okay, we can have a break in just a minute. I guess I'll look at your code and see if we can figure that one out. Okay, so I've just made this. So now we have a new file in the directory, pure Python. That's an executable. So if I just run pure Python, 0.3 seconds. So I haven't had to teach you how to annotate your code. You just ran shedskin and 0.3 seconds. And so the best we got to with straight Python without messing around with the math was 4.1 seconds, and then by expanding the math we got down to 0.26 seconds. Here we haven't expanded the math and we're down to 0.34 seconds. So that's quite a big win straight away. And if I take shedskin, what's it called? Shedskin, yeah, 2.py into here. So I'm going to, the shedskin 2 that I've got here, this is simply a version. It's just a copy of the other one where I expanded the math. That's all this is, just to show you what happens when we expand the math in here. No other changes. So we've We just ran the shed skin, didn't we? So now we can make it. So now we're making the version with the expanded math. And it'll take it a moment. And then if I run shedskin 2.py, then 0.21 seconds. So now by expanding the math, for whatever reason, I don't know what the difference is between the Python output and the shedskin output. I haven't gone in to go through the C code. But for whatever reason, this compiles and runs slightly faster than the Python output. But we've done this in 10 minutes. You haven't learned anything. You just learned how to run the command line call. So this is really nice. If you've got a problem that fits into this, so you're not using NumPy and you're not heavily dependent on third-party modules, particularly you've got a function or set of functions that you can extract, which are your bottlenecks, and you can compile those, Shedskin should do this for you cleanly without any code changes, and you should just get somewhere between a 10 and 50 times speed up. Now I'll just show you the last example. Let me remind myself how to run this. So right. C64 main. So I'm going to run the Commodore 64 emulator in straight Python. This is not compiled at this point. It's a bit slow, runs at about 2 frames a second. Oh, did I? Damn. Let's run it correctly. Minus tape equals. Yeah. So we're going to run this, and we're asking it to load International Karate Plus. Who remembers International Karate Plus? Oh, at least 3 of us. Perfect. Right. So I lost a lot of hours as a kid getting good at International Karate Plus. Who had a Commodore 64 as a kid? Yeah, okay, right. So you remember the scrolly coloured lines and things, right? So this is a full Commodore 64 emulator written in pure Python. So this is quite an impressive feat anyway, but obviously it runs a bit slow. I'm sure sooner or later it will run in PyPy, but right now, as far as I know, it doesn't because it depends on the PyGTK module, and that's not supported, as best I know, in PyPy at the moment. So let's get rid of that because it's horribly slow. Let's just go into the directory and move. So I'm not going to compile this live. It takes about 1.5 minutes to compile. It's introspecting 5,000 lines. So I pre-compiled this, and I'm just going to run the pre-compiled version. And there you go, full time, real time, effectively. So we've gone from 2 or 3 frames per second up to about 120 frames per second. So we get a 50, 60 times speed up. And again, this happens fully automatically. And the way that Mark Defer, the author of Shedskin, gets past the limitation that external modules like GTK are not supported in Shedskin, it's just that he took the CPU-bound code, actual emulator code, pushed it into a submodule, compiled all of that, and then had the PyGTK wrapper call into that code, which is just a module. It doesn't care that it's compiled in C++ and it's not straight Python anymore. It just calls into that module. So,
How long does it take to analyze the source code?
so the first time I did that, it took about 1.5 minutes. A year ago, Mark had a bunch of assumptions in his code. He could only analyze files up to a couple of thousand lines, and people said, this is never going to scale. About a year ago, he revisited those assumptions and just made those numbers big and realized that his algorithm was efficient enough. It's some kind of abstract source tree representation. He's up on all the papers on automatic type inference. Yeah, he's a good guy. He's smart, and he's done a lot of work on this. I just followed it over the years, and he revisited the assumptions, expanded all the numbers, and straight away went from it takes half an hour to compile the Commodore 64 example, and that's the hardest thing I can do, and then a post the next day saying, it takes 1.5 minutes, and it's not trivial, but it's not hard anymore. I'm a bit surprised at how far this has come on, and it was just one of those nice little comments. But one of the problems is no one ever talks about this, so no one ever shows this thing off, and it's a 60 times speed up for no work, which is amazing. But also it doesn't support NumPy, so it's got a limited use case in one of the areres where we'd love to make it really useful.
While using such
Interesting question. So the code that comes out should be the same, effectively the same as the Python code. So there is no support for threading or multi-processes, so none of the conditions that would apply if we got rid of the global interpreter lock should apply here. So as far as I know, it's absolutely correct. I've certainly seen no discussion in several years on the list of race conditions or other weirdnesses creeping in. When bugs do occur, Mark and the crew there fix them very quickly, but certainly I've seen none of those kind of issues popping up on the lists. But then we only have one CPU support, and that's a bit of a problem. Okay, so I think I'm going to call a break here, just a 10-minute break, and then we're going to push on after the break. Yeah, we're going slower than I expected, so there's a bunch more material. We're going to cover some of this. There's the online copy of everything, and then I'm free all this weekend to talk it through as well. Let's just take a 10-minute break now, get a cup of water, and then we'll push on. So I'm going to start again in 10 minutes flat in here. Okay, thank you. So we've got an hour and 20 minutes until lunch. I think I'm going to cut off the NumPy vector stuff probably. Maybe I'll just do a quick demo at the end. What we're going to focus on is NumPy, using it as a data holder for serial computations, and then integrating that with Python, and that gives us the really nice speed up that I want to get to. And then switching over to multi-processing and multi-core, or multi-machine rather, and hopefully running it in a small network across a bunch of machines here in the tutorial. So, half of you have been using NumPy in the past. Generally speaking, there's not much point using NumPy if you're not using vectorized calculations. How many of you have got a background with vectorized calculations, say with MATLAB or similar? Okay, not so many of you. So that's something we'll cover very briefly at the end. All we're going to do now is convert the pure Python code to use a NumPy vector as a data holder, just like a pure Python list. And then it's going to run slow, really, really slow. We'll have a look at why, because this is one of the beginner mistakes when someone hits NumPy for the first time. And I figured that as half of you have used NumPy and half of you haven't, we should have a quick intro to the way to make it go really slow and bad. But then we can work through how to make that go faster, and then how to go really fast with it. So we need to switch now to... where's my NumPy version? So gvim NumPy loop. So you've got NumPy loop as one of your base files. And I'm just going to run this because it's going to take a little while. So NumPy loop.py. As I said, all we're replacing is the Python list with a NumPy vector, which is a NumPy list. It's the same code as we had before. The calculate Z is exactly the same as we had before, very deliberately. All that's changed is down in the preparation routine, so that's calculate. All that's changed is I've added a couple of extra lines where we make a NumPy array from the original Python list. So we had the list Q and the list Z. Now we have QNP and ZNP. These are NP arrays. And the NP array right at the top, we import NumPy as NP. So if you've got the NumPy underscore loop.py example, you've got this code already. You could... I added an array to calculate Z. Yes. Yeah, and yes, and I also, because we make the output array in calculate Z, we make a NumPy version of the output array in there as well. So we now have 3 NumPy arrays, whereas before we had 3 Python lists. So intuitively, you'd be very correct in thinking NumPy is the really fast math library. It's really good at handling data. It represents it all in a C-like representation. All I've done is convert my Python list, which has got to be a bit slow, into a NumPy vector, which has got to be a bit fast. And then you're going to run the code, and we'll get the same output. And all we're doing is passing in, down here, calculate Z, QNP, and ZMP, so the NumPy versions of the Python lists. But then you'd be shocked that it takes a minute rather than 12 seconds. And you could very sensibly throw your hands in the air and shout, "Why?" And be rather annoyed. It turns out the reason is simple. What's going on behind the scenes is that by calling into NumPy, you're adding layers of abstraction that you have to call through. So it's not just the Python layers you have to call through, we also have to call through the C layers that are compiled in NumPy. The whole point of NumPy is that we give it a large lump of data, and then we call a function on it and just say, just calculate, just go and deal with it for me. And it happens all in C very fast behind the scenes. When we start iterating one item at a time over these lists, we end up calling calling NumPy through many layers to extract a zero-dimensional array of one item, which is our complex number, passing it back up through all the levels. We do an operation, then we pass it back down through all the levels and store it in memory, and then we get the next one. We pass it up, calculate down. So we're adding twice as many layers as we would have if we were just doing it in straight Python. And so I checked this with Travis, Oliphant, who's one of the founders of the NumPy project, and he said, sure, if all you're going to do is iterate with a for loop over your data, you can expect a 5 times slowdown. That's just kind of accepted. And they want to improve that, but it hasn't been improved yet. But it's the wrong way to use it. So if you just switch to a NumPy data type and iterate over the contents, expect a slowdown, and you're not going to like it. There's a way around it. There's a simple way around it. So if you make this change, please, so in calculate Z, where we dereference ZI, rather than returning a NumPy zero-dimensional array, so a complex 128 data type, which is a NumPy array, we're just going to convert it into a Python complex number. So rather than then asking in the calculations that follow, the Zi equals Zi squared plus Qi, down below, rather than asking that to go through all of the layers of NumPy, dealing with the complex 128 data type on the NumPy side, instead we're just converting it into a complex number. So this is just the little cheat to show you that nothing too weird is going on. It's just the fact that we've got these zero-dimensional arrays. So I save this. I go back and run that. And that's running quicker now, so you just see it on the screen. So Zi equals the complex of the Z square brackets I and Qi complex Q square brackets I. We're almost there. And so there we go. Now we're back to 12 seconds. So 12 seconds down from 1 minute. The only change is that we're casting this to a Python complex number rather than a NumPy complex data type because we're iterating one item at a time. So I wondered about whether I skipped this, and Travis said I really ought to show it to you because for anyone who's not used NumPy before, if you go in via this route, you might be confused and pretty annoyed that it runs so slowly. This is why, and this is how you get past it in the trivial case when you're converting your code. Really, we want to start doing more things with it, like dressing it up in Python, so we can go in faster. And I think we'll skip the profiling on this. But at this point, you could do the profiling, and you would see that all of the slowdown suddenly occurs, before we do this complex transition here, all of the slowdown occurs in this line, and it runs 5 times slower than the previous version. And that'll be a pretty good hint to you as to where the problem is. So now let's work on integrating Python with NumPy. And here's where you're going to have to scratch your heads a little bit, and we'll work through it. So you want a new directory, please, Python NumPy loop. And in there, we're going to just copy the NumPy loop example, the one we've just used. And let's copy the Python pure Python, the setup file that setup.py file we used in the previous Python example. Copy that over as well. No. get rid of some of these vims. Oh, damn. Right, so you've now got a Python numpy loop folder. It's got the numpy loop code in there. Let's go in there. We're going to get rid of that complex change I made a moment ago because we're not going to need that very soon. And then we'll extract out the function and run it to the Python process that we were using a moment ago. And I think import numpy and setup.py. So there's one change you have to make in setup.py. I think we just do import numpy. We'll test that in a second. So anyone have a problem at this point? Are we ready to carry on? Good? Right, so let's make a calculate z.pyx, the same as we did before. And then we're going to extract our calculate z method, just like we did before. So we're going to make the same changes. So we're going to have to import calculate z. And call calculate z dot calculate z in this case, yeah. So calculate z dot calculate z, method name change from that version of the file. And in here, what do we need? We need to import something. Python numpy. We don't need to import anything. So if I just test this works. What am I missing? That's what I was thinking, but I haven't got it in that version. Why would I not have it in that version? Okay, that's what I needed to know. So what do I want to add here? Import numpy as np. Perfect, thank you. So, we've got basically what we had before, so we'll just refresh. We've got the numpyloop.py module where we import calculate z. We've taken out the calculate z method and put it into calculate z.pyx. And down in the calculate method, we're referring to calculate z.calculate z. And the only difference between this version and the previous Python version is that we're using the numpy array, np.array, rather than the straight Python lists. But the argument list for calculate z is the same as it was before. And we've just got the reference to output equals np array in there. So We can run the Python on this, and then we get our HTML output. We can open that in Firefox, and we get a whole bunch of yellow lines, as expected. And if we run Python setup.py build ext in place, so now we get to the point that we've compiled the NumPy version of the pyx file using NumPy in Python, so that's the NumPy Python integration. That happened a bunch of years back. Now we get to the new compiled module. So we have calculate-z.so. And then if we run NumPy loop, this is going to run, let's see what speed this runs at. Okay, so this is going to run at the really slow speed, and the reason is that we're still dealing with all of the layers of NumPy code that we have to work through. Now, what I would like to do next is direct you at the NumPy Python tutorial page, which you can scan through, and we'll work through building up the Python code that annotates the NumPy version of our code here to make it run really, really fast. We can go quite a long way, and we're not going to have time for that, so we're just going to cover some of the basic stuff. And first of all, I want you to have a look at the page. So I'll direct you at the page. So let's just check. That did take 50 seconds. So rather than a minute, it took 50 seconds. It was slightly faster, but still way too slow. So you want this page here, docs.python.org, source tutorial numpy.html. If you search for Python NumPy tutorial, I think it's the second result. And this page, whenever you're working with NumPy in Python, you're going to love this page at the beginning. I probably lived in this page for the first couple of days of doing it to make sure I fully understood what was going on. There's a lot of information tucked away in here. So what I want you to do is just scan through the first couple of screens, and then we get to the bit about adding types. And here you get to see how we start to dress up the pyx file by importing the right type. So, for example, import numpy as MP. And up on screen, I'll pull up the annotated version, and then we can work through it and improve your code. So which one shall we work on? So we've already imported NumPy. We want to C import NumPy as MP. So how about that for our first change? So first change, calculate z.pyx. You want to change import NumPy as MP to C import NumPy as MP. And then let's go back and compile and just test that that's compiled. So yeah, so we need to also import. At this point, we need to have both imports there, don't we? What am I missing there? So under extension, yeah, okay, so we want to change our setup.py file as well. Right, So change your setup.py file as well. We need to give it a bit of extra information. Let's leave out the OpenMP bits for the moment. So all you actually need is the include dirs directive, telling it where to find numpy. And so at this point, if you run the Python setup.py buildx in place, then you should get a compiled calculate z.so without any errors. If we get any errors, we need to fix them at this point. And the reason I point you at that tutorial page and why I'm making sure we work through this by hand now is these errors that you've just seen me go through here will hit this each time we do this. It's slightly non-intuitive, and you just have to have the right setup in place to work with NumPy in Python. And it's worth going through the pain first of all and spotting some of the errors and knowing that they're easy enough to solve. So does anyone have any problems at this point? Do we have a working version? Okay, so I've run that. And if we just run, so I've compiled, I'm just going to run the NumPy loop version, and I think it'll be pretty slow still. Yeah. Who's talking? Oh, sorry, go on. Yep.
So is it, are you overriding your C import before we do import?
Yeah, now do I need that now? That might have been a kludge one I tried to fix. Let's get rid of that because that's too slow. Ooh. Okay, yeah, it's not needed. Sorry? Yeah. So you're telling, what's going on behind the scenes here? So we have to tell Python where to find the NumPy libraries. That's why we changed setup.py to have the include directories. And we have to give Python, the compiler wrapper, the information about the C import for the Python NumPy wrappers. And on the Python side, it needs to know where NumPy is. So we have two types of import going on so that both sides can see where the code is. And I think we can get rid of this in a little while, but at this point, because we haven't decorated things very well, I think we need to do this. Oh, possibly. Let's try that. Okay, yeah. So yeah, we just, I guess, I think when we go a bit further on, because
You only need C import for CDEF?
I think when we start cdeffing with the NP arrays shortly, I think we need it there. So I'm going to leave it up there. Ooh.
So then, which is NP bound to? I mean, it's,
So NP is bound on the Python side to NumPy, and on the Python side, the C import of NumPy. Depends on which part of the compiler process is involved. We're annotating it so that the different parts of the process can see what's going on and find the libraries they're expecting. So let's make some changes. Now I guess the first one to go through, let's go through, right, so here's the first change. Rather than receiving objects Q, max, hitter, and Z of any type, we're going to specialize them So Q and Z that's off the side of the screen, they're both going to be np.nd arrays, double complex, with dimension 1. So you just need to copy this line in. And then maxiter can be an int or an unsigned int. We don't care about that at the moment. Right, I'm just going to compile this and check, and then we can switch back. Okay. Yep, I'm just calling up. I'm checking I've just compiled it right. Calculate z.pyx. Okay. Yeah, sure. Is that okay? So setup. Non-type error on extensions. So what does that mean? Import numpy, you've got that.
My build here. Get this different non-type.
Let's just verify the code. Okay, so everyone's setup has the extension with include dirs numpy.getInclude, and then build ext, that hasn't changed from before. And we've imported numpy at the top. So we've all got that, right? Say again? Okay, and in the pyx, all we've changed is calculate z. We're decorating the 3 input arguments. So the easy one is int maxiter, and q and z are both np.nd array, double complex, ndim1. So single dimensional of type complex double, not complex single, and they are numpy n-dimensional arrays where ndim is specified. Does everyone have this at the moment? Any problems? No? Okay, so I've compiled it. I know that it works. Let's just run it. I think we're a little bit faster now, but still pretty slow. Yeah, still pretty horrendously slow. And let's call it up. So I did Python -a, and that generated, so Python -a calculate z.pyx. That gives us calculate z.html. And then if we open this up, so what do we have? So we can see that we've decorated things. I know that's not going to get any faster. Output we haven't specified. So whenever we put results into the output item, there's an awful lot of code associated with that. So we can specialize that in a moment. The range we can improve. We can cdef I in a moment. And then also we should cdef the zi and qi down here. So let's make some of those changes. Right, so the extra change, 2 new variable declarations, cdef, unsigned int, I. You could do I, comma, iteration rather than 2 lines there. Then if we go back, I'm just going to use Python on that. And call up the Firefox result. And if we compare these two, now what have we changed? We must have changed something. Sorry, what was that? Line 15. Oh, so yeah, so we've declared for the modulus operator. We still haven't defined Zi and Qi, so they're not going to be much faster. Has anyone run it and seen a speed difference? Yeah?
The for loop is changed.
The outer for loop. Oh yeah, okay, so the range operator was changed there as well. Yeah, because we pre-declared I again. Okay, so that's a bit faster. And then if we improve Zi and Qi, so we want to annotate those items. So we want, oh, that's the wrong version. Well, sorry, from 1 minute 5 seconds to? Oh, from 1 minute to 5 seconds. Okay, that's quite a nice improvement. Okay, so let me let's check that. Okay. Okay, 7 seconds. Yeah, okay. That's a good improvement. And I wish I could tell you that I knew that was coming, but I remember working through this line by line before, and it wasn't always intuitively obvious where the speed-ups were coming from. When delving into the C code afterwards, you can see what's going on, but first time through it, certainly a bunch of it is a surprise. So I've got a little recipe here where I'm working through how to get to the best result, but yeah, I didn't see that line coming, though, that change coming, and I haven't broken down the timings on a line-by-line basis, so that's kind of a nice result. Okay, so, now we want, how do we define this? CDEF, complex, double, ZIQ. I'm just guessing at this, let me just compile that. Oh, heck. Is it double complex? There we go. So CDEF double complex ZIQI. This should get rid of some more of the yellow for us. And I'm going to, so I've compiled that. Let's just run that. So I had 7 seconds down to 4 seconds. And if we run that through Python, so now we get the new HTML. And then let's have a look at the difference from the last to this one. So what do we see? So the first difference is Zi and Qi. They were pale yellow, and now they're white. So they're fully happening in C, which is nice. Any other differences? Oh yeah, so Zi equals Zi squared plus Qi. That's now Zi equals Zi squared plus Qi, but all in C. So we've gotten rid of a few more layers of dealing with the Python virtual machine. So we're now just operating in memory, in C, without any of the Python VM being involved. So what do we want to improve next? So output, we haven't given that a type. And abzi, probably going to leave that. Yes, it's just output we need to define now. So before I call up the code for my annotated output, do you want to have a guess? So we've passed in Q and Z, and we've annotated those up here anyway. And so down here, we just need to make a definition for output. So do you want to have a guess? Type in what you think will be the way to annotate output, or declare its type, the line before it's used. So just as we've typed in CDEFs for the unsigned int and the double, you want one for output as well. So have a quick think about it. Sorry? Well, so so output, as we have here, it's an array of integers. Up here we've declared an array of complex numbers of double type of dimension 1. This is a dimension 1 array, different data type, or different fundamental data type, but same idea. Now, saying that, I'm going to guess as well. But I might be guessing wrong. I haven't written that line in a good few weeks. Okay. So maybe that's a bad... How did I define it before? Okay. Okay. So cdef np.nd array int dimension 1 output. Oh, and then I pre-allocate it. Okay. So there's an extra optimization. So we declare an ND array of just the type integer, just the same as when we passed in the complex numbers, double complex, dimension 1, and its name is output. And then we're predefining it to be empty. So this is numpy is empty. We'll have to import that in a moment. Data type is integer, and the shape is one-dimensional, same length as Q. So all you're saying is make an array that's as long as Q, integer, full of zeros, empty. And to import empty, we need that one there. So, key what, sorry? Yeah. In fact, let's try np.empty. Let's try and compile. And then if we run that, what are we up to now? Okay, 4.2, so slightly faster still. Okay. Let's look at the annotated output. So the declaration involves a lot of Python calls, fair enough, that only happens once. The abs call, that's still expensive on ZI. Is there another way? Yeah, and there's no easy way around that at this level. And what I have to do, so what we have to do to go beyond this, if you remember back to the Python, pure Python example, the way to go significantly faster, so we're running at 4.2 seconds, and the way we got to with Python, pure Python, with the complex data type, was 4.1 seconds. So we're down as fast as we were with pure Python now, with numpy ND arrays. And the way to go faster was to expand the math. And so we're going to expand the math, and then we're going to go a bit further, because we can, now that we're using numpy arrays. So I'm just going to show you this bit. No need for you to type stuff in. Let me just get the right outputs. So I just want to copy loop. So I'm going to overwrite my local one. So this is the one that I was using to copy from a moment ago, and it's got some stuff in here about OpenMP that we'll look at in just a minute. And what you'll see here is that we've expanded the complex data types into double precision floating point numbers, and then we use them for the calculation down here. So this is just the same as the one I showed you an hour ago where we expanded the complex math. So let's, first of all, we'll just put it through Python and open it up. So as you can see here, Previously, we had a bottleneck in the innermost part of the loop on abs zi. So this was the reason this routine was running slow. Now that we've expanded the math, we get rid of that bottleneck. So there's no yellow in here now. A tiny bit of pale yellow here with some dereferencing, and that's all. So when we build it and then run it, there we go. So 0.23 seconds. So just by expanding the math, and this is just the same as we had before, right? We went from 4.1 seconds with the Python, pure Python version down to 0.26. Here it's 4.3 seconds down to 0.23 seconds. So that's a nice improvement. But it's still running on a single core. And this is kind of where some of the problems come in. So which version do I want to run? So if I run 1,000 and let's just say 20,000. So there's the 8 cores on my machine. So if we just run that and let it go for a bit, we see one core climbing up and maxing out for a little while, and then the calculation is complete. And then there's our result. So that's fine, but I've got 8 cores. I'd really like to use all 8 cores. We all know that inside Python we've got the global interpreter lock, so we know that Python is not designed to be multi-threaded or support multi-CPUs for CPU-bound problems. It works great with I/O-bound problems, but it doesn't work it doesn't work basically with multi-CPU support for CPU-bound problems. Each CPU could be used, but it will just do a bit of work on one, and then a bit of work on another, then a bit of work on another, never utilizing all of them. We need to get away from the global interpreter lock if we're going to parallelize nicely. What we'll look at after this with straight Python code is the multiprocessing module, where we spawn different Python interpreters, one per core, and run the code in parallel that way. What we're going to use right here with Python, and I'll just show you this, we can use OpenMP support, which is the C++ Fortran standard for multi-core support, where it'll compile code that can run on multi-cores at the same time, just with a couple of lines of changes. And then we can get a really nice speed up. So let's push this down out of the way for the moment. So I've imported, so this came in, I think it didn't exist in 0.14, which existed early last year when I was doing the EuroPython tutorial, and it was introduced in the last year, the p-range operator, so the parallel range. So this lets a range declaration, which one am I using? This one here. So rather than iterating serially, so one loop at a time on one core, we can use the p-range operator to use multi-cores, and we're specifically declaring that anything calculated on one core will not affect the result calculated on a different core. So we have to have a very parallel problem. We have to know that if we calculate that Mandelbrot plot from top left to bottom right, or bottom right to top left, or randomly, in whatever order, no result will influence the calculation of another result. If that condition holds, we can calculate it all in parallel. Potentially, we could take all 250,000 pixels that are shown there and calculate them in a one-er on a machine with enough cores. Okay? If that condition holds, we can make this run nicely in parallel. So all I've done here is import the p-range operator, and rather than declaring for I in range length q, I say for I in p-range length q, and I tell it no GIL is true. So this is the flag that says we're using numpy data types, so our data is stored in a numpy array. So it's not under Python's control, it's under numpy's control. And I'm declaring that the global interpreter lock doesn't have to get involved here. I'm saying that we can run threads in parallel on this underlying block of C code and on its memory, and everything will run in parallel, and there'll be no corruption. And so that's my declaration to make. So I'm going to save this. So if we run the Python -a, we're not going to see any change. It doesn't care that it could run in parallel. This is purely... what have I done wrong? I need to... We also have to tell Python that it doesn't need to do bound checking. That condition has to be true for p-range to be supported. There we go. So that's going to run the bigger version. So if I kick that off, that will happen. That looks like only one core still. Why would that be? Well, you can tell me that looks like one core, and I'd have to agree with you. What have I missed? Fine P range. Ah, of course. To simplify the setup, I commented out the OpenMP support, which was a bit silly. Right. It's going to force it to rebuild because it doesn't see that the setup.py file has changed. So I get rid of the generated one. I ask it to build again. There we go. Right, and now there we go. So now we see a much smaller hump on the right-hand side with multiple cores involved, but clearly not super well optimized, right? One of the cores bumps up to 100% briefly, and a couple of them bump up to something briefly, but they don't all bump up at the same time. So this is not fully utilizing the 8 cores in my machine, just some of the cores, some of the time. And we can do better than that. So we've gone from, that was 1.5 seconds. This is the larger version of the problem. So we were 4.7 seconds down to 1.5, so that's about 3 times faster. So it's using about 3 of my 8 cores to do things in parallel, which is a great win when all we did was change the compile options a little bit and import the p-range operator and specify that there. But we want to do better. So it turns out we have the option, well, OpenMP gives us the option of specifying different schedulers. And this area becomes a little bit of a black art. I think there are 4 options. And by default, you let OpenMP specify the one that it thinks works best on your problem. And so I just played with the 4 versions, and one of them works much better. The one I've chosen here from memory, OpenMP's parallel threads are allowed to say, I'm empty, give me work. And so more work is provided. So I've got 8 cores. That means 8 threads are going to sit there and say, I'm empty, give me work. And there are 250,000 iterations worth of work that could be provided out. So here, all 8 cores are just going to flag, I'm free, please use me. So let's save that. Build it again. And then if I run that, this time we should see all 8 cores just briefly peak up there. So there we go. So now we're down to about 0.7 seconds, so from 4.5, and there we see all of the cores bouncing up for as much work was available as possible. And we can run much larger instances of the problem, and we end up with this machine just getting a bit too hot and shutting down. But all of the cores get used all the time. So as long as you've got adequate cooling and big enough fan, it's quite nice to have all of your cores maxing out, running at C speed in parallel, totally poning the problem and just working it as hard as possible. So with this version of the code, and this is all in the GitHub repo, I end up, we go from 12 seconds from the pure Python version, I end up getting down to 0.04 seconds, which is a 297 times speed up. And that's the best that I can get at the moment out of this 8-core machine. But I think a 300 times speed up is pretty worthwhile for an hour's effort or so learning this stuff. Yes. Yes, you have the scheduling, the atomic locks, the barriers, you have access to that via Python as well. I think you have some access. I don't think all of it's exposed. But from memory, yeah, there's a page that popped up late last year on the Python wiki. From memory, enough of the primitives are exposed there that you can pretty much protect most of your code in the same way that you would in C. I don't know how far it goes. I didn't get into that. So the question there was, with OpenMP, you're able to specify things like barriers so that you say, I want all of this to run in parallel, but some of these results depend upon other results that are running in parallel. So you can calculate this bit after this other bit, and these variables can be shared across local cores running in parallel. These variables are private to each thread. And so you have that support in OpenMP, and it gives you very flexible support for running things in parallel. The question was, is that supported by Python? From memory, most of it is supported in Python. I don't remember all the details, but there's a good wiki page on that. Right, now that I've given you a 300 times speed up, I've exhausted all that I can do going down the compilation route. So let's do some parallel processing in a really lightweight fashion. So now we're going to leave Python behind, at least for now. No, we're going to leave Python behind. So now we're going to have a little bit, okay, we've got 30 minutes. We've got time to have a little bit of fun on one machine and across several machines. So let's get rid of the old stuff. Right, you go away. You go away. And that's everything. All right, let me just catch up in here. Okay, so now we're going to work with the multiprocessing module. Hands up if you've used the multiprocessing module. Okay, only about half of you, all right. So with the multiprocessing module, we have a really easy way of telling a Python instance to spawn sub-Python instances, which have their own reserved memory space, the same as any other Python instance. And you can give it parts of a problem to solve. So you can take a large problem, decompose it into parts of a problem, and in my case, we're going to spit out 4 or 8 versions running in parallel, let them all run in parallel, and then pass the results back up to the parent. The parent recombines the results, and then gives us a finished result. So that's a totally thread-safe, memory-safe, no race condition, no worry way of spawning out virtual Python processes, which will run in parallel for you and then give you a finished result. The overhead, of course, is that we are spawning sub-Python processes. So we end up with a 5 to 20 meg or so interpreter for each one that's spawned out. And there's a memory overhead. We have to take a copy of memory, pickle things up, send them out, reinstantiate them, run, and then pickle the result and pass it back up to the parent, and the parent has to recombine this. So there are some overheads. But as you'll see when we get to the code, code's really simple. And the guy who wrote, I forget the guy's name, the guy who wrote the parallel Python module that we'll use in a moment, used pretty much the same interface as the multiprocessing module. And with the parallel Python module, we can run not only on one machine, but also on multiple machines, and multiple machines with multiple Python interpreters. So we could run some with Pycon, some with CPython, some with Jython. So we can really mix everything up, and we have this really simple stepping stone with the multiprocessing module to get things prototyped and working first of all. So we need multi.py. So we're going to walk through this code first of all, just so you can see the couple of lines that are different. So open up multi.py if you would. So we have the same show method at the top. That's boring. We calculate Z serial pure Python. One change. Rather than 3 input arguments, we now input a tuple, and we expand the tuple to 3 input arguments. Now I forget if it's multiprocessing or parallel, I think it's multiprocessing. I had some weirdnesses with passing in multiple arguments, so I ended up passing in an argument which I expanded to the full argument list. Yeah, I can't think of the details from that from EuroPython. So for this example and for the parallel Python example, we use just 1 input argument and expand it. But otherwise, the code is exactly the same, straight from the pure Python that we started with right at the beginning. Same setup. What we do differently down here, and this is the only significant difference, we declare how many chunks of work we want. We're just going to work with 1 chunk, which is all of the items, first of all, just to show it running on 1 CPU. And then we're going to split it down. So based on the number of chunks of work we want, we've got this large item, we're going to split it. So if we had 4 items of work, we would split it into 25% sublists. Then we generate these chunks of work. And all we're doing here is taking the large list and just picking enough elements out to fulfill the number of chunks that we want, accepting that if we don't have a list that divides by 4, for example, that we want to have 3 lists of the same length and 1 that has all the remainder items without any left over. We want to have 4 lists only of roughly the right size. Then we use multiprocessing to create a pool. So this creates a set of Python interpreters that are running and waiting for work. we use the map async function call, passing in the method that we're going to run and all of the data, and it maps the data out to each of the Python instances, runs the data, and then we use a blocking get request. So this just says, get me all the data back, but wait for the Python interpreters to have finished running. So once they've all finished, the data comes back, we then recombine them into the output list, and then we have the same output list that we had before, but this time composed of all of the subparts that we've just pulled back together, and then we show it on screen. So running that with 1 would be really boring. So let's just change that to 4 first of all. So let's just check this works. So if I run, there we go. So now I'm running 4 Python interpreters in the background, and you can see top right that I've got a bunch of CPU activity. There were 2 cores that did most of the work by the look of it, and a couple that did some of the work. Should that not be 4? Maybe 1 was hidden. Oh, interesting. I'm going to run that again. Let's have a look at the Python list here. So where's Python's running? Too many Pythons to make that really obvious. Well, anyway, we can see that we had, okay, a couple of chunks were small maybe, and a couple were the right... Why were 2 running there? No, I just divided into 4. No, I just took the 250,000 items, which is the list length we've been dealing with, and they divide it into chunks of 4. And someone tell me, 250k, that subdivides by 4 cleanly, doesn't it? I'm not being stupid here.
Different parts of the image take longer to render.
Yes, and that's if only. Yeah, if do you know more than me there? Do you know what the answer there was? You said, so I remember the problem here now, and if I'd have only looked at the slide, I would have reminded myself, but I don't know it in relation to OpenMP with static versus dynamic.
It's just that here, like they said, different parts of the image take different time.
Absolutely.
Dynamic, it can make that.
Is it statically deciding up front in OpenMP how to okay, and that makes perfect sense, right. Okay, thank you. Okay, yeah, so I like having a bright audience. You can fill in the gaps for me. Right, so where's my output? So the problem is, we've divided this into 4 chunks. So think of it, first quarter, second, third, fourth, right? All of this area takes no time to calculate. So the one who's dealing with this set of rows just zips through, has a bit of hard work here, and then zips through the end. The 2 that are running through here zip through and then have a lot of hard work that takes a while and then zips through the end. And so that's the 2 running through these, and then the 4th one that runs in no time runs through, clips that bit, and then runs out the far end. And so that's all that's happening here. We've said give me 4 static, and this comes back to the static versus dynamic scheduling for OpenMP, 4 static lumps of work. I'm going to give you no hint as to whether it's easy to compute or hard to compute. You're going to subdivide it into 4 lumps and just schedule them. And if 2 of them take longer than the other 2, well, that's just tough. You've got 8 cores. Between 4 and 6 are going to be underutilized, and that's just the way it is. Now, there's an easy way around that, of course. So let's just make sure this runs for you guys. So can you please call up multi.py and change the number of chunks to, let's say it fits your number of cores. This won't solve the problem, but it will help to solve it. So if you've got 8 cores, put 8 in and just run it. Sorry? Yes, and that's the next, the line that's commented out. Yeah. So, and that's because I wanted to start with 1, 2, 4, 8, 16, 32. And so I just override it there. But yeah, you can do the same. Uncomment that second line if you want. So if you just run that and call up your system monitor, you can see a number of cores being used. Some of them being used more than others, given the complexity of the area being calculated.
When you want more chunks than cores by some multiplier, so then
And we're just getting there. Or by some multiplier. I mean, it comes down to... Exactly, yeah. So here, I'm just going to show 4, and then 8, and then 16, and 32. And I think 16 and 32, there's no real difference in speed. Or maybe it's after 32. But yeah, we end up with me coming up with a heuristic and saying, well, yeah, if I double the number of cores that I've got as amounts of work, then even though some cores finish soon, we end up with all the work being done correctly. And yeah, it's whether it's double or...
Well, I mean, if you've got more chunks than cores by a multiplier, then it'll interleave. Like the first 4 chunks were all scanning across the top where it was easy.
Yep.
And all the
Sure.
cores got an easy run, and
Yeah.
all the cores get a hard run.
Yep. Yeah, sure, yeah.
It's actually not quite as black and white, because I've done this from large data processing.
Ah, okay.
The problem if you spawn lots of processes is you can run out of memory,
Yep. And we definitely hit that here from memory.
not very pleasant. Also, you're going to start losing time because the OS is going to be context switching too fast.
Sure.
So what I found worked was to set up a work file model.
Set up.
A work file model, I spawn exactly the number of processes equals the number of cores,
Uh-huh.
less a deflation factor if you're on hyperthreading because those aren't built for it.
Yep.
And then let the cores contend for access to jobs.
Yep. Okay. Yeah, and again, it comes down to problem-specific heuristics that fit your kind of data. The physics problem I mentioned at the beginning, I ended up going all the way through to getting that running on CUDA machines. And so I had a 480-core GTX 480, touched on this at the end. And that's because configuration for the problem was a couple of kilobytes. It ran for about 50 seconds, and it output a couple of 100 bytes. And it used almost no memory during the processing. It was purely CPU bound and embarrassingly parallel. So it's a beautiful CUDA problem to solve. Whereas I've worked with numerical flood modeling, computational fluid dynamics, and there you end up memory bound, CPU bound, contention for transferring local information around the whole kit and caboodle, and that's just horrid and takes a while to get your head around.
Does the number of chunks and the number of processes have to be the same, or can you decouple those? There are more chunks than processes.
Oh, sure. So I've got 8 cores here, and as you mentioned, I've got 4 real cores and 4 what's the term? Hyperthreading or fake cores, yeah. And so with the fake cores, what you're saying is there's a lump of silicon on a real core that might be underutilized. There could be the int processing units and the float processing units. If all of the int units aren't being utilized, we can make a virtual core that looks like a whole nother core. And then when int jobs come through, we can push it through the real core. But if you end up with everything being float bound and all the float units are being utilized, the fact that you've got 8 cores being presented means you've got 4 real ones that are fully utilized and 4 that are trying to squeeze in the gaps on the spare bits of silicon. So you don't get 8 times performance, you get 4 plus a fraction performance. I get about 6 times performance on here for this problem. So I've got 8 cores, of which 4 are real. I'm going to specify 32 chunks of work in this case. Just run that. And now we'll see all of the cores being busy most of the time, but you still see some of the cores finish work early, and some of the cores finish work late. And so we could go to 64 or 128 or whatever and increase it. But then we start spawning, then we've got larger amounts of memory that we're passing around between processes, and we can end up with memory contention issues. So
Can you have chunks that wait for work?
well, and then you're getting into a scheduling process. Here we're not worrying about that, but yeah, the next level is here's 1 million items of work, and here's 10 machines with a variable number of cores and clock speeds and utilizations during the day. Please efficiently schedule these 1 million chunks of work onto these machines and give me the result back a couple of hours later. But then you need a job scheduler, and then you can then look towards, say, MapReduce or Disco is a nice lightweight one in Python. Write your own job scheduler that fits the problem. That's what I did with the physics problem a while ago. Yeah, there's a number of options there. I'm not worrying about that in this tutorial. Okay, so we've got 15 minutes. So what I want to do now is transition from, so you've all run the multi.py demo, right? And it runs across your cores. That's a nice little win. So let's run across a bunch of machines. To remind myself how this works. Parallel Python pure. So I want you to make some changes which are going to mirror this, and then we can calculate across a bunch of machines as well. So as I mentioned, the multiprocessing module makes this, that forces us to do the first piece of work. So in this version, I've got the same calculate Z serial pure Python. It takes an argument chunk and then expands the tuple. So we don't have to change that. We're still using, in this case, I use the multiprocessing module to count the number of cores. And the chunk size is the same. So what we need to do is change what's down here, and we import, so we need to import PP. So just import PP, that's the parallel Python module. And then the chunk calculations are the same. What changes is, rather than having the multiprocessing pool section, which sends out the results via map async and then combines the results with po.get, instead we change that bit of code slightly to look like this. So I need you, between start time and end time, you want this block of code rather than the block of code that you've got in multi. In fact, which bits of this can we get rid of? We can get rid of... no, you need to type that in. Yeah, pp servers equals empty brackets, so that's an empty tuple. We make a job server, so that's a pp.server, and we're telling it which servers it can use to do work. And so we're just telling it to use the local machine. Then we submit all the jobs using calculate Z serial pure Python. So that's the function, and parallel Python works a bit differently. This lets us specify a function that should be pickled and sent over the wire, either internally to the other cores or over the wire to other machines. We give it a tuple of input arguments. So here it's a tuple with one argument chunk. We tell it modules it depends upon, and it cares about no other modules. And I forget what the last argument's there for. What else would it depend on? Maybe it's modules to import, and other functions that it needs to import from this module that needs to be pickled. We're not depending on any other functions in this module either, so we haven't got to pickle anything else. So we submit these jobs, these pickled jobs, to the job server, and then we add them to a list, and then we're going to monitor the jobs, make sure that they're running in parallel, combine the result. This is the same as po.get in the last example. And then we've got an output list, which is all of our data that's come back to us. So this is a nice, simple, well, bunch of lines to type, I appreciate, but a simple enough transition from the multiprocessing example a moment ago. I'll run this in a second. How many of you are actually typing this in? One of you. There must be more than one of you. Oh, you've got it from GitHub. Okay, fine. Yeah, even better solution. Yeah, sorry, I should have included this in the distribution as well. I was thinking we were going to have more time to transition between the code, but I don't want to run into lunch. So yeah, grab it from the GitHub repo. If you just search for GitHub and Oswald, you'll find my link up there. So whilst you're grabbing that from GitHub, and it's in the parallel Python directory, parallel Python, pure Python. Let's just see if I run that. So here I spawn out a number of jobs, and we see all the cores in a pretty similar way to what we had before working. So at this point, it's just doing the same kind of job that we had a moment ago. Let me call up the Right, now I'm setting it up so that it's going to run over the network with a bunch of machines. So, what's my... Ah, now, of course, you guys are on the Wi-Fi, aren't you? Duh. Okay, I remember hitting this point at EuroPython as well. All right, let's try. So someone tell me, what's the Wi-Fi access point? Just Pycon. Oh, same IP address. Is that right? Can someone give me their IP address? Who's going to run the code? I'm sure.
I'm actually behind that on my VM.
Oh, damn. Okay, who's not behind a VM and a NAT?
10.36, 255, 84.
Maybe if you've got a, you may not have a ping server running though. Oh, I know. Somebody run minus. Oh, what's the arg I need? PP server minus auto discovery minus debug. Right, can some of you have got it? Run pp server.py minus a minus d. Sorry? Minus a minus d. A is for auto discover, so I can find you, and minus d is for debug. Just puts out log messages so you can see what's going on. All right, this is slightly experimental. And let's set that to 0. Let's try. So if I try parallel Python, pure Python. Okay. Now I think I'm just finding... Oh, that would be annoying if I can't get this to work at the end. Didn't I just say use no CPUs? Number local CPUs is 0. PP servers is... I'm not running a PP server. What's your IP address? Go for it. What? 10? .36 200, so 250 165. 65. Okay, let's try. Is that still running locally, or is that running? Do you get any jobs? Good grief.
In the example code you have on Git,
Yeah.
it's PP servers and then in quotes star.
Ah, thank you. Like that?
Star comma.
Yeah, star comma. But why am I still running on? I don't want to start with number of jobs. Number of local is set to 0. Why would that not set to 0? Yeah, blast. Python pure Python slash what did I miss? I'm really sorry. I'm missing something really obvious here. All right, I probably should dwell on that. Well, I can tell you what would have happened. So where we got to at EuroPython, when I was on the same network as everyone I was teaching, I had a MacBook, regular MacBook, 2-core, old, slow, one of the slowest machines in the room at the time, and I was running it with 6 people on the network, and we spawned out, I don't know, 60, 70 jobs across the machines, and we set a much bigger job size, and then you hear all the fans kicking up and all the machines participate in the work, and then we get a nice collaborative display coming back, and then that was the crescendo of the tutorial, and that was a nice way to end that part of it. So I promise you this does work. I used this in the physics company, and there we had 4 machines with 8 cores each, 3-point-something gig machines, and we had all of those running maxed out doing the X-ray high-risk spectroscopy simulation work, and that was running at Christmas using PP Server. Now there's one hard-won tip that comes out of that. Where's my... Yeah, this tip. So how many of you might use the parallel Python module to run jobs in parallel, either on one machine or on many machines? Okay, a bunch. Okay, so you need to know this one. This will bite you. So in pptransport.py, there is a default socket timeout which is set to 30 seconds. What that means is any job that takes longer than 30 seconds looks like a machine that has been turned off or had its Ethernet cable pulled out, and the job server throws a totally uninformative error message and then resubmits the job, and then resubmits the job, and then resubmits the job. And it's really boring, and you're sitting there with a MacBook at home talking to Python, so Python 2.7 on a MacBook, Python 2.6 on a Linux box, spawning out your Mandelbrot jobs at midnight before you fly to EuroPython, wondering why the hell when you get to a certain job size you get these strange debug messages and nothing useful coming back. And it took me a while to trace it through and figure out there was a socket timeout. So in pptransport.py, I changed my socket timeout to be 24 hours, all right? Just a sensible big number, such that the problem doesn't occur. You have to change this in all the places where PP Transport exists. So not only on your machine, which will time out after 24 hours, in this case, talking to a machine, but the machines that are working as well. Otherwise, they time out after 30 seconds and give no answers back. So you want all of the machines timing out after 24 hours, such that your jobs that could take, with physics jobs, easily a couple of hours, certainly tens of minutes, you want all of these jobs running and returning the answers correctly. So just edit pptransport.py on all of your machines. As soon as you hit something that looks like a debug error, that, or a timeout error, sorry, that occurs over 30 seconds, search the Parallel Python forums, and you'll find I wasn't the only person searching for the same thing, saying, why is this message really uninformative? And then a bunch of other people just say, yeah, edit this timeout. I don't know why the timeout isn't a bigger number by default. It really feels like it ought to be. So I think... Well, exactly, yeah. And so something, I'm not going to get onto vectors. So one other thing we can do with Parallel Python, I'm not going to show you right now, is that as long as the modules are installed on your remote machine, so for example, your Python compiled.so modules, if they're on the remote machine in the directory where the code is being run from, you can refer to the compiled modules on your local machine and then run the compiled modules remotely. One thing we can't do, just coming back to the remote monkey patching, is automatically distribute the compiled SO files over the network. And that was something I was having a hack at for last year at Python. I didn't get it solved. I was kind of hoping it would be easy enough to wrap up with a bit of introspection, find the module that's being imported, binarize it, pickle it, send it, and then inject it into the namespace of the running process at the other end, such that you could then automatically distribute your compiled modules. It turns out it wasn't quite as trivial as I was hoping it was going to be, and I ended up not solving it that time. I didn't look at it this time. But I figure that's possible as well. But certainly if you compile things using Shedskin or Python and have them installed on the remote machines, they'll work fine. Yep. From memory, it's modules to import. So it only pickles up the function that you're sending, that you've told it about. It doesn't do any dependency checking. It needs to know if that function calls other functions and if it needs to import other modules.
So it's not like multiprocessing?
Which multiprocessing pickles everything by doing introspection. Parallel Python takes the whole file that you've written and just takes that text and sends that over the wire, and it assumes you're going to tell it all the bits it's got to fill in. So you have to do a bit of work manually. It's not quite as clean. It's got lower overhead when it passes the functions around, so it's faster, which is nicer, as long as you've got your head around the fact that you've got to pre-specify some of the things. I'm sure there's a middle ground. What I would love to see is something that automatically distributes the SOs and does the introspection, just takes care of all of it for you. I figure that could be kind of perfect. All right, everyone, so I'm going to call it there. One thing I didn't get onto is the use of vectors and PyCUDA. I'm totally happy to come and talk about this if you want to find me at some point. All the code's online. I'll put up a blog post on ianoswald.com, and then the contents of the PDF, that's all online at the moment. I guess in a couple of weeks I'll get that updated with this version, and then it should be 60-odd pages by then, hopefully. And if you want to find me tomorrow, I'm sitting in Startup Row with the new data mining AI vision startup project that I'm working on out of Startup Chile. So I'm going to be in wherever the Startup Row thing is on Friday all day, and I'm very happy to talk about that or about this. Just come and find me and have a natter, or buy me a beer and we'll talk some more. All right, thank you very much, everyone. I believe there's a feedback form, is that right? Do you know anything about the feedback forms that need... SurveyMonkey. Is there a link going around about that?